Hey guys, good morning and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly let me know in the chats. Quickly let me know in the chats. Good morning, guys. Good morning. Good morning. Good morning and welcome back. Good morning and welcome back. Perfect, perfect, perfect. So my dear students, as you all must be knowing, today we are going to do the complete class 11th Inorganic Chemistry. So it is going to be one mega marathon in which I shall be completing your whole Inorganic Chemistry of your class 11th. Okay. Well, the session duration is going to be like 8 to 10 hours. I don't exactly know how long it's going to take. It might take 8 hours, it might take 10 hours, right? Okay, so in between 8 to 10 hours, you can consider. That's going to be the session duration. And again, every single thing I'll be discussing from the scratch only, from zero only. I'll try to cover all the things, whatever can be asked from your class 11th in organic chemistry, right? Whatever concepts can be asked, I'll try to deal with all those concepts in the today's session right from the scratch. Okay? So already, let me know in the chats. Already, people, should we start the session directly without wasting any sort of time? Physical chemistry marathon will be done after this particular session. My next session is going to be your class 11th physical chemistry. Okay? And guys, one more thing, whatever things I'll be writing on the screen, I would want you guys to take a note of every single thing. Okay? Because every single thing is going to be equally important, right? When it comes to your NEET 2025 examination. Perfect? Again, I'm repeating the same thing. Today, we are going to do class 11th in organic chemistry, not the class 12th one. Class 11th in organic chemistry will be completed in the today's session, not the class 12th one. Okay? I hope I'm clear to everyone. So people, the first chapter with which we shall be starting in the today's session is going to be your chemical bonding. Okay? Your chemical bonding is going to be the first chapter of the today's session. And you must be knowing this chemical bonding chapter, I would say this is the most important chapter of your inorganic chemistry. My dear students, every year, almost like 4 to 5 questions are asked from this particular chapter. You should know that. Every year, 4 to 5 questions are asked from this particular chapter. At the same time, if this particular chapter is stronger, then only your organic chemistry can become stronger. My dear students, if there is a problem in this particular chapter, your organic chemistry can never be strong. So first of all, from this particular chapter alone, 4 to 5 questions. Apart from that, this particular chapter forms the foundation, forms the basis of your organic chemistry as well. So I would want you guys to do this particular chapter properly, right? Wherever you feel any sort of doubt in between the session, you can ask me in the live chats, right? I'll try to help you out in order to tackle those doubts, whatever you'll be having in between the session. right? And today's marathon is directly going to be your exam oriented. No unnecessary things. Whatever concepts can be asked in the question in the examination, right? Only those concepts we shall be discussing right from the depth, right? There are a lot of other unnecessary, irrelevant things in the chemical bonding too, which are not asked in the examination. I'm not going to deal with them at all. Okay? So let's get going then. Let's get started with the today's session. So my dear students, we are starting with the chapter chemical bonding. First of all, if I ask you, what is a chemical bond? How do we exactly define the chemical bond? My dear students, chemical bond is nothing but, it is the force of attraction. Chemical bond is nothing but, it is the force of attraction. I would say that force of attraction which holds the constituent particles. That force of attraction which holds the constituent particles together in a molecule. That force of attraction which holds the constituent particles together in a molecule. So any force of attraction which holds the atoms together in a molecule, right? Which holds the constituent particles together in a molecule, you'll be calling that force of attraction as the chemical bond. Point number one. Okay? So chemical bond is nothing, it is just the force of attraction that holds the constituent particles together in a molecule. Now, my dear students, the first type of chemical bond, what do you call that as? You call that as ionic bond. What is an ionic bond? Understand what exactly ionic bond is all about. My dear students, for example, I'm taking an ionic compound NaCl over here. It is the most typical example of the ionic compound, NaCl. It is a common example of the ionic compound. Now, first of all, in case of your NaCl, as you can see, how many elements do you see? You have got two elements here. One is sodium and one is chlorine. You must be knowing sodium is metallic in nature. Sodium is example of a metal and chlorine is example of a non-metal, right? Well, you must be knowing metals have got the tendency to lose electrons. Non-metals have got the tendency to gain electrons. Metals have got the strong tendency to lose electrons. Non-metals have got the strong tendency to gain electrons. Now, my dear students, if you talk about this particular sodium over here, sodium, as you must be knowing, it is your group first element. It belongs to group 1. It is an alkali metal, right? Since sodium is a group first element, so I would say in its outermost shell, there will be only one electron. Now, since sodium is metallic in nature, metals have got the tendency to lose electrons, and this sodium has got only one electron in its outermost shell. So people, I must say, sodium is going to lose that outermost electron and will get converted into Na positive, right? In the similar way, if I talk about chlorine, chlorine is your group 17 element. Chlorine is your group 17 element. It has got 7 electrons present in its outermost shell. And people, if chlorine has got 7 electrons present in its outermost shell, I would say the electron that is lost by sodium would be gained by chlorine and will get converted into Cl negative. Okay. So on one side, formation of Na positive has taken place. On another side, formation of Cl negative has taken place, right? So my dear students, can I say over here, I got equal and oppositely charged species? I got equal and oppositely charged species over here. And you know, between the oppositely charged species, which force of attraction will arise between them? I would say there would be electrostatic force of attraction between them. There would be electrostatic force of attraction between them. And my dear students, this electrostatic force of attraction between this Na positive and Cl negative, the electrostatic force of attraction between this Na positive and Cl negative over here is what you will be calling as your ionic bond. You will be calling as the ionic bond, or you can call it as the electrovalent bond as well. You can call it as the electrovalent bond as well. So what is the ionic bond? What is the electrovalent bond? I would say ionic bond, electrovalent bond is nothing. It is just the electrostatic force of attraction between the cation and the anion. That's all, right? And my dear students, if you see carefully, can I say sodium lost its one electron completely? Chlorine gained that one electron completely. So I would say whenever ionic bond formation takes place, there would be complete loss and gain of electrons. So whenever ionic bond formation takes place, there would be complete loss and gain of electrons. Perfect. I believe you got the concept of what is an ionic bond. Now, my dear students, what are the favorable conditions? What are the favorable conditions for the formation of ionic bond? What are the favorable conditions for the formation of ionic bond? The first and the basic point. My dear students, for the formation of ionic bond, I must say one element should be metallic in nature so that it can lose electron, and another element should be non-metallic in nature so that it can gain electron. Because once the metallic element loses electron, then only cation formation takes place. Once non-metallic element gains electron, then only anion formation takes place. And once cation anion is formed, there would be electrostatic force of attraction between them. You will be calling that electrostatic force of attraction as the ionic bond. So for the formation of ionic bond, I must say one element must be metallic and another one should be non-metallic. Point number one. My dear students, point number two. I would say the metallic element, it should have low ionization energy. Metallic element should have low ionization energy. What does that mean? That means for the formation of ionic bond, you should have the metallic element, you should have the non-metallic element. What does metallic element do? It loses electron. What does the non-metallic element do? It gains electron, right? Now, my dear students, lesser the ionization energy of metallic element, easily will be the formation of cation. And if the cation is getting formed easily, I would say ionic bond would be getting formed easily, right? As simple as that. So for the formation of ionic compound, for the formation of ionic bond, I must say the metallic element should have low ionization energy so that it can lose electron easily, so that it can form the cation easily, right? Okay. Similarly, the non-metallic element, it should have high electron affinity. Why non-metallic element should have high electron affinity? So that it could gain electron easily and formation of anion takes place easily, right? Okay. So these are the three conditions which you must remember, right? When it comes to the favorable conditions for ionic bond. One element must be metallic, another should be non-metallic. Metallic element should have low ionization energy so that formation of cation would be easy. Similarly, non-metallic element should have more electron affinity so that formation of anion takes place easily, right? And once formation of cation and anion is taking place easily, I would say ionic bond formation would be easy at that point of time, right? I believe this is clear to everyone. Right, people? Am I clear with this? Quickly in the chats. Perfect. Now, my dear students, regarding ionic compounds, what are your ionic compounds? Ionic compounds are the ones which contain ionic bond in them, right? Now, there are some characteristics of these ionic compounds, some important features of these ionic compounds, which you must remember. First of all, in case of ionic compounds, there is ionic bond present. What is ionic bond? It is the electrostatic force of attraction between the cation and anion. Since electrostatic force of attraction is very strong in nature, if electrostatic force of attraction is strong in nature, so I would say your ionic compounds, they would be generally hard. Due to the strong electrostatic force of attraction, I would say they would have high melting points and boiling points as well, right? Due to the strong electrostatic force of attraction in solid state, the ions cannot move, right? Due to the strong electrostatic force of attraction in solid state, I would say the ions cannot move. If ions cannot move, I would say in solid state, these ionic compounds, they behave like insulators. In solid state, they behave like insulators because there is a strong electrostatic force of attraction between the ions, due to which the ions cannot move. If the ions are not moving at all, I would say they are going to behave like insulators in solid state. But remember, when it comes to the molten state or aqueous state, in molten and aqueous state, they behave like conductors. In molten state and aqueous state, they behave like good conductors of electricity, right? And people at the same time, due to very strong electrostatic force of attraction, I would say, due to very strong electrostatic force of attraction between the ions, I would say these ions would be packed very closely. And if the ions are packed very closely, I would say their density would be definitely high. Their density would be definitely high. So these are some important features when it comes to your ionic compounds. Due to the strong electrostatic force of attraction, due to the strong electrostatic force of attraction, I would say they are generally hard. Their melting boiling points are high. In solid state, they behave like insulators. In molten and aqueous state, they behave like conductors. And due to the strong electrostatic force of attraction, their densities are higher. Okay? I believe this is clear to everyone. Now, my dear students, there are some terminologies which are related to these ionic compounds. Some terminologies which are related to these ionic compounds. What these terminologies exactly are? The first terminology which is related to your ionic compound, that is your lattice energy. Okay, lattice energy, which I represent with delta H lattice. What is lattice energy exactly all about? What is lattice energy exactly all about? My dear students, I can define lattice energy in two ways. Number one, I can define lattice energy in two ways. Number one, the amount of energy released, when 1 mole of an ionic compound, the amount of energy released when 1 mole of an ionic lattice is formed from its constituent gaseous ions. You can see this is Na positive here, this is Cl negative here, right? So these are unlike charges basically, right? And between the unlike charges, there will be attractions. Due to attractions, energy is always released. Due to attractions, energy is always released. So I would say, during the formation of 1 mole of an ionic lattice, from its constituent gaseous ions, whatever is going to be the amount of energy released, that amount of energy released is what you'll be calling as lattice energy. That's what you'll be calling as lattice energy, right? My dear students, since energy is released during this process, and that particular process in which energy is released, you call that particular process exothermic process. And for exothermic processes, delta H value is coming out to be, delta H value will be coming out to be negative, right? This is one way of defining the lattice energy. The amount of energy which is released when 1 mole of ionic lattice is formed from its constituent gaseous ions. Point number one. Well, I can define this lattice energy in one more way as well. I can just define it in the reverse way. I can say it is defined as the amount of energy. It is defined as the amount of energy required. It is defined as the amount of energy required to break 1 mole of an ionic lattice into its constituent gaseous ions. into its constituent gaseous signs. So basically, I can define lattice energy in a different way as well. Let me just do one thing. Let me just reverse this reaction. If I reverse this particular reaction, what do I get? I'll be getting something like this. NaCl solid gives Na positive gas plus Cl negative gas. If you look at this particular reaction now, if you look at this particular process now, what is happening exactly? I can say I am breaking down 1 mole of ionic lattice. I am breaking down 1 mole of ionic lattice into its constituent gaseous signs. I am breaking down 1 mole of ionic lattice. I am breaking down 1 mole of ionic bond into its constituent gaseous signs. And since I'm breaking the force of attraction between Na positive and Cl negative. I'm breaking this force of attraction between Na positive and Cl negative. So I would say energy would be required in this particular process. If energy is required here, I would say this particular process would be endothermic in nature. And let me tell you, the amount of energy which is required to break 1 mole of lattice into its constituent gaseous ions, that's also what you will be calling as delta H lattice. And my dear students, I must say here, it is endothermic in nature. So delta H lattice, its sign here would be positive. I would say magnitude wise, both are going to be equal. It is just their sign is reversed. Their sign is opposite. Okay. I hope this is clear to everyone. I hope this is clear to everyone. So either you want to define lattice energy in this way or this way. The choice is all yours. The amount of energy required to break 1 mole of ionic lattice into its constituent gaseous ions, or the amount of energy released when 1 mole of ionic lattice is formed from its constituent gaseous ions. Okay? Perfect. Again, I'm repeating the same thing here. Delta H lattice would be negative. Here, delta H lattice would be positive. Magnitude wise, they are going to be same. It is just their signs are opposite here. This negative sign tells you that energy is released. This positive sign tells you that energy is absorbed during the process. Okay? Perfect. Now, my dear students, lattice energy. Lattice energy. It gives you the idea about the stability of the ionic compound. Lattice energy gives you the idea about the stability of ionic compound. Okay? It's very much simple. More the lattice energy of ionic compound, more the lattice energy of the ionic compound, that means more energy is required to break it. If more energy is required to break the ionic compound, that means ionic compound does not want to break. That means ionic compound is very stable. It is thermally stable. As simple as that. As simple as that. More the lattice energy, that means more energy is required to break the lattice into its constituent gaseous ions. If more energy is required to break the lattice, if more energy is required to break the ionic compound, that means the ionic compound does not want to break. If the ionic compound does not want to break, that means ionic compound is more stable. As simple as that. So remember, your lattice energy and stability of ionic compound, they're directly related. More the lattice energy, more the stability of the ionic compound. Now this lattice energy, it depends on 2 factors. Lattice energy depends on 2 factors. Number 1, lattice energy is directly proportional to the charge on the ions, inversely proportional to that of size of the ions. Directly you can remember these things. Your lattice energy, I would say it is directly proportional to the charge present on the ions, inversely proportional to the size of the ions. Right? So more the charge on the ions, more is going to be its lattice energy. Lesser the size of the ions, more is going to be its lattice energy. For example, tell me the answer of this particular question. My dear students, you have got LiCl, NaCl, KCl, RbCl. First of all, this lithium, sodium, potassium, rubidium, they are your group first elements. Chlorine is your group 17 element. So this is technically Li positive, Cl negative, Na positive, Cl negative, K positive, Cl negative, Rb positive, Cl negative. Cl negative everywhere is same. So I'm not going to give my answer on the basis of Cl negative. I'll be giving my answer on the basis of the cations. Now people, the charge on every cation is same. The charge on every cation is same. So my answer won't be on the basis of charge. My answer would be on the basis of size. Simple. So this is lithium, sodium, potassium, rubidium. When you talk about lithium, sodium, potassium, rubidium, down the group, what happens to size? Down the group, size increases. And if size increases, your lattice energy, automatically that will decrease, right? Lattice energy would decrease. So which of the following has got minimum size? Lithium. Minimum size, more lattice energy. Lesser the size, more the lattice energy. So this is the order of lattice energy here. Now MgO, NaCl, LiCl. So here, if you look carefully, this is technically Mg di positive, O di negative. This is Na positive, Cl negative. Li positive, Cl negative, right? If you look at all these three species, look at the first species. In the first species, the magnitude of charge is more. In the first species, the magnitude of charge is more. So lattice energy and charge, they are directly proportional. More the charge, more the lattice energy. So lattice energy of the first one is going to be maximum. Now, among NaCl and LiCl, you are not going to decide on the basis of anion. Decide on the basis of cation. Lesser the size of cation, more the lattice energy. So I would say, if this is number 1, this is number 2, this is number 3. So MgO has got maximum lattice energy, followed by your LiCl, followed by your NaCl. This is the order over here. This is the order of the lattice energies. I believe this is also clear to everyone. As simple as that. Okay. Now, my dear students, there is one more thing which we have, that's hydration energy. Like we defined lattice energy, in the similar way, we are going to define the hydration energy. What is meant by hydration energy? What is meant by hydration energy? What is meant by the hydration energy? Have a look, guys. See, first of all, if I talk about hydration energy is defined as, it is defined as the amount of energy, released when 1 mole of gaseous ion undergoes hydration. What does that mean? Try to understand very carefully what exactly I'll be doing. My dear students, imagine this is the container which I have. And imagine that in this container, I'm keeping water. Let's say there is water. This container is full of water. For example, if this container is full of water, so these are the water molecules which we have. These are the water molecules which we have in this particular container. Okay. Now, my dear students, imagine that, or let's do one thing first of all. In case of water, between oxygen and hydrogen, which one is more electronegative? Oxygen is more electronegative. So I would say oxygen everywhere will have delta negative, hydrogen will have delta positive charge, because oxygen is more electronegative. If oxygen is more electronegative, it would have attracted the bonded pair of electrons towards itself, right? So everywhere oxygen would be having delta negative charge. Now people, imagine that I'm introducing Na positive here in this container. Imagine that I'm introducing Na positive here in this container. When Na positive would be introduced, what do you think? Can I say the negative part of water, will start interacting with this Na positive? The negative part of water will start interacting with this Na positive, right? So can I say there will be attraction between the negative part of water and this Na positive? There would be attractions. And due to the attractions, energy is always released. Due to the attractions, the energy is always released. Now let me tell you, this particular process over here, this phenomenon is what you call as hydration. Now the amount of energy released, when one mole of gaseous ion undergoes hydration, amount of energy released when 1 mole of gaseous ion undergoes hydration is what you call as hydration energy. As simple as that. Okay. So what is the hydration energy? Hydration energy is nothing but the amount of energy released when 1 mole of gaseous ion undergoes hydration. Now, my dear students, since energy is released during the process, I would say hydration is exothermic in nature. If hydration is exothermic in nature, I would say delta H hydration would come out to be negative. Again, simple. Delta H hydration would be coming out to be negative. Now the point is on what factors this hydration energy depends upon. People, it's pretty much simple. Your hydration energy, again, like your lattice energy, it is directly proportional to charge on ions, inversely proportional to size of ions. Directly proportional to charge of ions, inversely proportional to size of ions. So more the charge on the ion, more water molecules will be associated with the ion. If more water molecules are associated with the ions, I would say more energy is released. If more energy is released, that clearly tells you more is going to be the hydration energy. That's it. Okay. Similarly, lesser the size of the ion, more is going to be the charge density on the ion. Lesser the size of the ion, more is going to be the charge density of the ion. And more the charge density of the ion, more water molecules can be associated with the ion. More the water molecules being associated, more would be the hydration. That means more would be the hydration energy in short. Am I clear with this? Am I clear with this, people? Okay. Now you're going to tell me the answer of all these questions. See guys, I've got Li positive, Na positive, K positive, Rb positive. They belong to same group. And down the group, size increases. More the size, lesser the hydration. Or I would say lesser the size, more the hydration. So which one undergoes more hydration? Li positive undergoes more hydration. Li positive undergoes more hydration. If Li positive undergoes more hydration, more energy would be released at that time. That means more would be the hydration energy. Okay, number one. Number two, Li positive, Na positive, K positive. What about the size order? This is the order of their size, right? Because down the group, ionic size increases. Now, if they ask you about the hydrated size, that means, hydrated size means when you introduced Li positive in water, I would say water molecules got associated with Li positive. This Li positive. Now, the size of Li positive including these associated water molecules, this complete size, this overall size, Li positive plus the size of the associated molecules. This is what I call as this hydrated size of Li positive. This is what I call as the hydrated size of Li positive. Now, among Li positive, Na positive, K positive, Rb positive, which one undergoes more hydration? Li positive undergoes more hydration. So towards Li positive, more water molecules will be associated. If more water molecules are associated with Li positive, I would say more would be its hydrated size. So what would be the order of the hydrated size here? This is going to be the order of hydrated size. Okay. What is going to be the mobility order? See guys, Li positive aqueous, since its size is maximum, it's the most bulky group here. It's bulky. If it is bulky, its tendency to move, its tendency towards motion would be less, right? So mobility order would be this, right? And my dear students, more the mobility, more the conductivity. Lesser the mobility, lesser the conductivity. So I would say conductivity would follow the same order, because more the mobility, more the conductivity. Lesser the mobility, lesser is going to be the conductivity. So these are the different types of the questions which can be asked when it comes to your hydration energy. Nothing apart from all this. Okay? Perfect, guys. I believe I'm clear to everyone. Okay? Now, my dear students, till now we have discussed how many concepts? We have discussed ionic bond, favorable conditions of ionic bond, lattice energy, hydration energy, right? Okay. Now comes The next topic, what is that? That is how to draw the Lewis structures, and how to calculate the formal charge. This is again one of the topic from which questions are frequently asked. And it's a very simple topic. How to draw the Lewis structures, as well as how do we calculate the formal charge of different atoms. As I told you, it's a very simple topic, guys. See, what do we need to do? For example, I'm taking carbon monoxide, CO. This is the molecule. I need to draw its structure, and I need to know what is the formal charge present on oxygen, what is the formal charge present on carbon. How do I exactly do it? Understand properly what I'll be doing. People, just tell me one thing. How many valence electrons are there with carbon? Carbon, you know, has got 4 valence electrons. How many valence electrons are there with oxygen? Oxygen has got 6 valence electrons. So in total, how many valence electrons are there? There are total 10 valence electrons. Okay? There are total 10 valence electrons. If there are in total 10 valence electrons, if I ask you, how many valence electron pairs will be there? How many valence electron pairs will be there? One pair contains 2 electrons. So I would say there are 10 valence electrons. That means how many valence electron pairs are there? There are 5 valence electron pairs in total. If there are 5 valence electron pairs in total, what you need to do exactly is, let's say this is your carbon, this is oxygen. What I'll be doing, I'll be putting a single bond in between them. Single bond means I've used 1 electron pair between carbon and oxygen. I've used 1 electron pair. How many electron pairs I have in total? 5. Out of 5, how many I have used? I've used 1. How many valence electron pairs are left? 4 valence electron pairs are left. Now people, among these two, which one is more electronegative? I would say oxygen is more electronegative. If oxygen is more electronegative, start filling the octet of oxygen. I would say 2, 4, 6, and these two are 8. So octet of oxygen is complete. Now, how many valence electron pairs I had? 5. Out of 5, how many I have used? 1, 2, 3, 4. 4 I have used, right? 4 I have used. So 1 electron pair is left as such. Give that 1 electron pair to carbon. Now people, octet of oxygen is complete, but octet of carbon is not complete. Carbon right now has got 2 plus 2, 4, only 4 electrons. Now we need to complete the octet of carbon as well. So how do I exactly complete the octet of carbon? What I'll be doing, I'll be removing one of the electron pair on oxygen, and instead of that, I'll be putting a bond. Let me just remove one more electron pair of this oxygen and put a bond in between them. Perfect. Now check whether the octet of carbon as well as oxygen is complete. Yes, the octet of carbon as well as oxygen is complete. So this is the structure of your carbon monoxide as per your Lewis. Okay. Now, my dear students, if this is the structure of your carbon monoxide, the point now is whether there is any charge on carbon, whether there is any charge on oxygen. How exactly do we do that? Have a look, people. So, for example, I want to calculate the formal charge on carbon. How do you calculate the formal charge? Right now, I want to calculate a formal charge on carbon. My dear students, in non-bonded state, if I ask you, how many valence electrons carbon has? Normally, in non-bonded state, carbon has got 4 valence electrons. Minus. Right now, how many valence electrons carbon has? 1, 2. Out of these two, I'll just consider 1. Out of these two, I'll just consider 1. Out of these two, I'll just consider 1. So 2 plus 3, 5. So 4 minus 5 comes out to be minus 1. So the charge, the formal charge on carbon here is minus 1. Okay. Similarly, if I ask you, what is basically the formal charge on oxygen? What is the formal charge on oxygen? Oxygen in non-bonded state has got 6 valence electrons. In non-bonded state under normal conditions. Right now, how many valence electrons it has? 1, 2, 3, 4, 5. So 6 minus 5 comes out to be plus 1. I would say there is plus 1 charge on this particular oxygen here. Okay. People, I believe I'm clear to everyone. If I'm clear, let me know once in the chats. If I'm clear to everyone, let me know once in the chats. Everybody. Amazing, guys. Amazing. Perfect. Let me take a few more examples. My dear students, let's say we have got NO2 negative. Let's say we have got NO2 negative. If you look at NO2 negative, what exactly am I supposed to do? I want to draw the structure of NO2 negative first. After that, I'll be doing the calculation of formal charge of each atom. How exactly I'll be doing it? Just try to understand. What is my first step? As I told you already, what is my first step? Calculate the valence electrons. If I talk about nitrogen, how many valence electrons nitrogen has? Nitrogen has got 5 valence electrons. One of the oxygen will have 6 valence electrons. So 6 multiplied by 2. 6 multiplied by 2, right? There's a negative charge here as well. If there is negative charge, add that negative charge, right? So 6 to 12, 12 plus 1, 13, 13 plus 5 is 18. So there are total 18 valence electrons we have. Total 18 valence electrons we have. If we have got total 18 valence electrons, if I ask you, how many valence electron pairs do we have? I would say we have got 9 valence electron pairs, right? Now, my dear students, we just have to arrange these valence electron pairs. How exactly? Now see, NO2 negative. If I ask you among nitrogen and oxygen, which one is less electronegative? Remember all these points, guys. Whatever points I'm telling you, you need to remember all these points. So people, among nitrogen or oxygen, which one is less electronegative? Nitrogen is less electronegative. The one that is less electronegative, that will be considered as the central atom. So I would say the nitrogen here is the central atom. The one that is less electronegative, that would be considered as the central atom. So nitrogen is my central atom here, right? And we have got 2 oxygen atoms as well. Let these be 2 oxygen atoms. Okay. What is my first thing? What is my first thing? I'll be drawing a single bond. I'll be drawing 2 single bonds, right? One single bond, second single bond. That means how many electron pairs have I used? 1, 2. Out of 9 electron pairs, I've used 2 electron pairs. How many are left? 7 electron pairs are left. Now, I'll start filling the octet of more electronegative element now. I'll start filling the octet of more electronegative element now. Which one is more electronegative? Oxygen. So start filling the octet of oxygen. Start filling octet of this particular oxygen. See guys, 2, 4, 6 and 8. Its octet is complete now. Similarly, 2, 4, 6 and 8. Its octet is complete. How many electron pairs I had? 9. Out of 9, how many have used? 1, 2, 3, 4, 5, 6, 7, 8. So 8 electron pairs I've used. How many electron pairs are left? 1 electron pair is left. Give that 1 electron pair to nitrogen. Is the octet of this particular oxygen complete? Yes. What about the octet of this oxygen? Yes. What about the octet of this nitrogen? I would say octet of this nitrogen is not complete. As you can check, 2, 4, 6. So its octet is not complete. So what I'll be doing? Just select one of the oxygen atoms among these 2. Let's say I'm selecting this one. Remove one of the lone pair, and instead of that, you can put a double bond. So this is the structure of your NO2 negative actually. This is the structure of your NO2 negative actually. Now people, the point is, how can we check the formal charge on each atom? So first of all, let me calculate the formal charge on nitrogen. Let me calculate the formal charge on nitrogen. How exactly? Say guys, in the non-bonded state, nitrogen has got how many valence electrons? 5. In the non-bonded state. Right now, how many valence electrons nitrogen has? 1, 2, 3, 4, and 5. So 5 minus 5 comes out to be 0. So there is no charge on nitrogen. There is no charge on nitrogen. Let me call this as oxygen number 1. Let me call this as oxygen number 2. So if I ask you, what is going to be the formal charge of oxygen number 1? What is going to be the formal charge on oxygen number 1? My dear students, oxygen in non-bonded state has got 6 valence electrons. Right now, it has got 1, 2, 3, 4, 5, 6, and this 7. So 6 minus 7 comes out to be minus 1. So formal charge on this particular oxygen is minus 1. Now, if I again ask you, what is the formal charge on the second oxygen? You can calculate that too. So oxygen in non-bonded state has got 6 valence electrons, and right now it has got 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So formal charge on this oxygen atom is 0. Right? So this is how we can draw the structures of different molecules, and we can calculate the formal charge of the atoms present in the molecule. If I'm clear, let me know once in the chats quickly. If I'm clear, let me know once in the chats quickly. Everyone. Guys, I'm teaching entirely from basics. And I'm teaching you the required stuff. What will be asked in the exam, I'm just talking about that stuff. Nothing more, nothing less. Okay? Perfect. Let me give you one more example. With that, we'll move ahead. Let's say we have got O3 molecule. Let's say we have got O3 molecule. Okay? O3 molecule. So people, let's exactly try to draw the structure of O3. Let's exactly try to calculate the structures of O3. Now, my dear students, in case of O3, how many valence electrons would be there? What do you think? If I talk about one oxygen atom has got 6 valence electrons. So 3 oxygen atoms will have 6 3s are 18. So there are total 18 valence electrons. If I ask you how many valence electron pairs will be there, there would be 9 valence electron pairs, right? Now you have got 3 identical atoms. So keep one in the middle and 2 at the terminal positions. Okay. Now people, try filling the octet of the terminal atoms. 2, 4, 6, and 8. 2, 4, 6, and 8. We had 9 electron pairs. Out of 9, how many we have used? 3, 6, 7, 8. Give 1 to this one. Since the octet of the terminal atoms is complete, the octet of the terminal atoms is complete, but the octet of this particular oxygen is not complete. So you need to complete the octet of this particular oxygen. How exactly? See, 2, 4, 6, right? Now, for example, I'm removing one of the lone pair here, and instead of that, I'm putting a bond. So this is how your O3 looks like. This is how your O3 looks like. This is how your O3 looks like. Now, people, calling this is oxygen number 1, calling this is oxygen number 2, calling this is oxygen number 3. What do you think? Will there be any formal charge on this oxygen? This oxygen in non-bonded state 6 valence electrons. Right now, 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is minus 1. So there is minus 1 charge on this oxygen. This particular oxygen in non-bonded state 6. Right now, 1, 2, 3, 4, 5. 6 minus 5 is plus 1. There is plus 1 charge here. 6 minus 6 would be 0. There is 0 charge on this particular oxygen. So this is how you can calculate the formal charge. This is how you can calculate the formal charge on different atoms. I believe I'm clear to everyone. Yes? Perfect. Is this concept clear, or you want to see more examples of this? Is this concept clear, or you want to see more examples of this? Let me know once quickly. Everybody. Someone is saying voice is not syncing with the video. Is that? Let me check. Voice is not syncing with the video. It's perfectly fine. I think you have something wrong with your internet connection. Okay? There's something wrong with your internet connection. You check it out. Someone is saying, sir, my teacher said Unacademy is a scam. Tell your teacher to stand for 12 hours and deliver a lecture. He does that, I'll salute him. Okay. All right. I'll take one more example. Let's see. Let's see whether you'll be able to do it or not. Dear students, for example, I'm writing Cn negative. Cn negative. Okay. Cn negative. People, let's try to do all the things about Cn negative as well. Let's try to do all these things about the Cn negative as well. What is the first thing which I'll be doing? What is the first thing which I'll be doing? The first thing is I'll be calculating the valence electrons. I would be calculating the valence electrons. Carbon has got 6 valence electrons. Nitrogen has got 5 valence electrons. There is a negative charge, so add it. So 5 plus 1, 6, 6 plus 6, 12. So there are in total 12 valence electrons. If there are 12 valence electrons, so how many valence electron pairs will be there? 6 valence electron pairs will be there, right? Now people, you have got Cn negative. Let this be carbon, let this be nitrogen. Put a single bond in between. Now, start filling the octet of more electronegative element. More electronegative is nitrogen, so 2, 4, 6 and 8. Out of 6 valence electron pairs, I've used 1, 2, 3 and 4, so 5 and 6. Octet of nitrogen is complete, octet of carbon is not complete. So let's try to complete the octet of carbon as well. So remove this lone pair and put a bond here. Okay. Right, people? I think I did a mistake. Oh, okay. I did a mistake. There is 4 here. Valence electrons with carbon are 4. Carbon have got 4 valence electrons. Just a second. 4 plus 1, 5. 5 plus 5, 10. So there are 5 valence electron pairs. 5 valence electron pairs. 5 valence electron pairs. Yes, there's a mistake. So this is C. This is N. Right? Start filling the octet of nitrogen. So 2, 4, 6 and 8. Right? Give 1 electron pair to this carbon. So all the 5 electron pairs have been used. All the 5 electron pairs have been used. But at the same time, if you look carefully, the octet of carbon is not complete. The octet of carbon is not complete. So remove this electron pair, put a bond instead, right? Remove this electron pair, put a bond instead. So now we can check octet of carbon as well as the octet of nitrogen is complete. Okay. Now, if I ask you what is the formal charge on this carbon? Formal charge on this carbon would be equal to carbon in non-bonded state has got 4 valence electrons. Right now it has got 1, 2, 3, 4, 5. So 4 minus 5 comes out to be minus 1. So formal charge on this carbon is minus 1. What about the formal charge on this nitrogen? Formal charge on this nitrogen would be in non-bonded state 5 valence electrons. Right now 1, 2, 3, 4, 5. So 5 minus 5 comes out to be 0. So there is no formal charge on this nitrogen over here. Okay. So this is how you draw the Lewis structures and this is how you calculate the formal charge as well. I believe every single thing is clear till here. Okay. I believe every single thing is clear till here. All right, people. All right. I'm moving on to our next concept, next topic. What is that? That's your Fajan's rules. Have you heard about this? As I told you guys, I'm directly moving on to the concepts. I'm just giving you those concepts which are required for the exam. Nothing less, nothing more. Okay? Nothing less, nothing more. Directly questions are asked from Fajan's rules. Now, first of all, what kind of information do we get from Fajan's rules? See, guys. And remember, I would say Fajan's rules are going to give us the idea about Fajan's rules are going to give us the idea about the covalent character, in an ionic bond. About the covalent character in an ionic bond. My dear students, all of you must be knowing, there is no bond between any two atoms which can be either 100% ionic or 100% covalent. No bond will be there which is either going to be 100% ionic or 100% covalent. Every covalent bond has got some ionic character in it, and every ionic bond has got some covalent character into it. Every ionic bond has got some covalent character into it, and every covalent bond also has got some ionic character into it, right? And this Fajan's rules, they are going to give us the idea about the covalent character in an ionic bond. Okay? They are going to give us the idea about the covalent character in an ionic bond. Now, I'm going to summarize this complete Fajan's rule in this particular slide itself. I'm not going to get into the details. I'm just telling you that stuff which is used to solve the questions, right? See, guys, as per Fajan's rules are concerned, covalent character in an ionic bond, it depends on two factors. Covalent character depends on the polarizing power. It depends on the polarizing power of what? Of the cation. At the same time, I must say, covalent character, it depends on the polarizability of the anion. So two new terms I'm introducing here. One is polarizing power, which is defined for cation. Polarizing power is also called as ionic potential. Polarizing power is also called as ionic potential, right? And similarly, polarizability of anion. So on two factors, covalent character depends on polarizing power of cation, polarizability of anion. Now, if I talk about the polarizing power, of the cation, let me tell you, polarizing power of cation, it depends on the charge on cation and it depends on the size of cation as well. Polarizing power of cation depends on charge on cation and inversely proportional to size of cation. If I talk about the polarizability term is first of all defined for anion, and it's directly proportional to charge on anion. At the same time, it is directly proportional to size of anion. These are few things which you need to know. Nothing more, nothing less. Few things which you need to know. Nothing more, nothing less. Polarizing power term is defined for cation. Polarizability is defined for anion. Polarizing power of cation is directly proportional to charge of cation, inversely proportional to size of cation. Polarizability of anion is directly proportional to charge of anion as well as directly proportional to the size of anion. Now, my dear students, one more thing. In case of D block elements, okay, leave this particular point as such for now. Let's me check whether you can solve these basic equations or not. Tell me, guys. Arrange in the order of their polarizing power. Polarizing power depends on two factors, charge and size. Now, Li positive, B di positive. Which one has got more polarizing power? More the charge on the cation, more the polarizing power. More the charge on the cation, more the polarizing power. More the charge on the cation, more the polarizing power. More the charge on the cation, more the polarizing power. More the charge on the cation, more the polarizing power. Simple everywhere. Simple everywhere. Now, if charge on cation will be same, then you will be deciding on the basis of size. Lesser the size of cation, more the polarizing power. Lesser the size of cation, more the polarizing power. Simple, right? Lesser the size of cation, more the polarizing power. Lesser the size of cation, more the polarizing power. Right? As simple as that. Now, my dear students, this is Fe dipositive, cobalt dipositive, nickel dipositive, copper dipositive. Fe dipositive configuration is 3d6. This is 3d7 configuration, 3d8 configuration, 3d9 configuration. Tell me just one thing. In case of these D block elements, in case of these elements, on moving from left to right, what happens to screening, shielding? What happens to shielding here? Quickly. See, first of all, your d orbitals, they are ineffective shielders. Or let me not talk about all this. Just remember one thing. On moving from left to right, effective nuclear charge here increases. Effective nuclear charge increases. And let me tell you, polarizing power of the cation, it depends on the effective nuclear charge of the cation as well. And more the effective nuclear charge of the cation, more is going to be the polarizing power of cation. Just a simple statement. More the effective nuclear charge, more is going to be the polarizing power. That's it. Okay? That's it. That's it. So, what is going to be the order of the polarizing power of these cations? This is going to be the order. I believe I'm clear with this. Now, below one more thing. When you move from 3D to 4D, 4D to 5D, when you move from 3D series to 4D series, 4D series to 5D series, what do you see generally? You see effective nuclear charge increasing. And effective nuclear charge, if increases, what does that mean? That means polarizing power also increases. That means polarizing power also increases. Right? And if I give you this question, zinc dipositive, cadmium dipositive, mercury dipositive, which one has got more polarizing power? You tell me. Which one has got more polarizing power? I would say this belongs to 3D, this belongs to 4D, this belongs to 5D, right? When you move from 3D to 4D, 4D to 5D, simple, effective nuclear charge increases, so polarizing power of the cation increases. Correct? Now, my dear students, tell me about the polarizability. Polarizability is defined for the anion, and polarizability is directly proportional to charge on anion, also directly proportional to size of anion. Now tell me the answer. N tripositive, O di negative, F negative. More the charge on anion, more the polarizability of anion. More the charge on anion, more the polarizability of anion. Right? F negative, Cl negative, Br negative, I negative. Charge everywhere is same. Talk in terms of size. More the size of anion, more the polarizability. More the size of anion, more the polarizability. So these are the polarizability orders. These are the polarizability orders. Okay. Now, arrange the following in the order of their covalent character. Arrange the following in the order of their covalent character. Before solving these questions, let me tell you one thing. Or let's try to solve this first. After that, I'll tell you a few more things. See guys, in these three examples, you can see zinc dipositive, Cl negative. Cadmium dipositive, Cl negative. Mercury dipositive, Cl negative. So Cl negative everywhere is same. So I'm not going to decide on the basis of the anion. I'm not going to decide on the basis of Cl negative. Talk in terms of the cations. Zinc dipositive, cadmium dipositive, mercury dipositive. Which one has got more polarizing power? Mercury dipositive has got more polarizing power. More the polarizing power, more the covalent character. So this is the order of the covalent character. Right? This is the order of the covalent character. As simple as that. This is zinc dipositive, S di negative. Cadmium dipositive, S di negative. Mercury dipositive, S di negative. S di negative everywhere same. This is 3D, this is 4D, 5D. So more polarizing power, more covalent character. Li positive, F negative. Na positive, F negative. K positive, F negative. Rb positive, F negative. Cs positive, F negative. So I would say F negative everywhere is same. F negative everywhere is same. Now this lithium positive, sodium positive, K positive, Rb positive, cesium positive. Charge on every cation is same. If you look carefully, charge on every cation is same. Now talk in terms of size. Lesser the size of cation, more is going to be the polarizing power, and more the polarizing power means more is the covalent character. So this is going to be the order, right? BeF2, BeCl2, this is BeCl2 here. BeF2, BeCl2, BeBr2, BeI2. What do you think is going to be the order of this particular question? Check it out quickly. This is beryllium di positive, this F negative. This is beryllium di positive, Cl negative. Beryllium di positive, bromine negative. Beryllium di positive, I negative. So I would say Be di positive everywhere is same. Now talk in terms of anion. F negative, Cl negative, Br negative, I negative. More the size of anion, more is the polarizability of anion. More the size of anion, more is the polarizability of anion. More polarizability of the anion means more is the covalent character. All these things I have told you already. I believe this is clear. Okay. Can you give me the answers of these questions? Can you check them out? Can you check them out quickly? Yes, Akhil, even JEE students can watch this video. Yes, why not? Quickly, guys. Done? Is it done or not? I hope all these questions you would have solved already. Yes? Now, people, if you check carefully, this Al, F negative, Cl negative, Br negative, I negative. See, Al tri positive everywhere is same, this F negative. Al tri positive, Cl negative. Al tri positive, Br negative. Al tri positive, I negative. So, Al tri positive everywhere is same. Now, talk in terms of anion. For anions, what do we define? Polarizability. More the size of anion, more is the polarizability of anion. More polarizability means more covalent character, right? This is F negative, Cl negative, Br negative, I negative. More polarizability of anion, more the covalent character. Again, the same order, and again here, the same order. Because everywhere you can give the answer on the base of polarizability of anion, right? I believe this is clear. And guys, there is one more concept here, which you need to remember. What is that? See, polarizing power of the pseudo inert gas configuration. Polarizing power of the pseudo inert gas configuration. Polarizing power of that cation which has got the pseudo inert gas configuration is always more than that of polarizing power of that cation which has got inert gas configuration. For example, what is the pseudo inert gas configuration? See guys, let's say if I talk about copper. What is the outermost configuration of copper? You should know it. 3d10 4s1. And this is argon here. Right? This is the configuration of copper. If I talk about the configuration of sodium, this is neon followed by 3s1. This is the configuration of copper. This is the configuration of sodium. Now guys, if I make them in the cationic form, CO positive, Na positive. So what am I doing? I'm just removing the last electron. Right? Perfect. My dear students, over here, if you look at this particular configuration, I would say in this configuration, this is the noble gas configuration followed by D10 configuration. Noble gas configuration followed by D10 configuration. Whenever any cation has this sort of the configuration, noble gas followed by D10. This particular configuration is what you'll be calling as pseudo inert gas configuration. Noble gas followed by D10 configuration is what you call as pseudo inert gas configuration, right? This is what you call as pseudo inert gas configuration. And this Na positive, what does it have? it has just got the inert gas configuration. And that cation which can form pseudo inert gas configuration, that cation which has the pseudo inert gas configuration has got more polarizing power, right? For example, look at this question. CuCl, NaCl. Which one has got more covalent character? Which one has got more covalent character? Lavanya, that's for chromium. I was talking about copper. Which one has got more covalent character? You need to answer, guys, this. You need to answer this. Absolutely. It's going to be CuCl, which has got more covalent character than that of NaCl. Why? Because Cu positive here would be having the pseudo inert gas configuration, and that cation which has got the pseudo inert gas configuration would be having the more polarizing power. More polarizing power means more covalent character. Okay, I believe all of this is clear, right? Perfect. Now some applications of Pajan's rules. Some of the applications of the Pajan's rules which you need to know. What are those? What are those? Dear students, let me tell you. Solubility of ionic compounds. Generally, you'll observe solubility of ionic compounds would be more than that of the solubility of covalent compounds in polar solvents. Solubility of ionic compounds would be generally more than that of solubility of covalent compounds. In what? In polar solvents. Or I can say something like this. I can say solubility is directly proportional to what? Ionic character. Solubility is directly proportional to what? The ionic character. Solubility of ionic compound is directly proportional to what? The percentage ionic character. And this ionic character is nothing but it is inversely proportional to covalent character. On the basis of this particular stuff, you can answer the question which we have given over here. My dear students, I want to compare the solubility of Ag2S with Ag2O. I want to compare the solubility of Ag2S with Ag2O. This is Ag positive, S di negative. Ag positive, O di negative. Ag positive is same. S di negative, O di negative. Charge on both the anion is same. Charge on both the anion is same. Now talk in terms of size. More the size of anion, more the polarizability, more the covalent character. So this is the order of covalent character. So what would be the order of ionic character? Ionic character order would be just reverse. Ionic character order would be just reverse. So this is the order of ionic character. And whatever is going to be the order of ionic character, same is going to be the order of solubility. So what is going to be the order of solubility here? So I would say Ag2S is a less soluble than that of Ag2O. Ag2S is less soluble than that of Ag2O. I believe this is clear to everyone. Now people, let's have a look on one more. Let's have a look on one more. If I want to compare the solubility of FeOH whole thrice and FeOH whole twice. This is iron tri-positive here. This iron di-positive here. On one side you have got iron tri-positive. On one side you have got iron di-positive. Now first of all, if I ask you about the order of covalent character. Order of covalent character is going to be this. FeOH whole thrice is going to be more covalent than that of FeOH whole twice. FeOH whole thrice is going to be more covalent than that of FeOH whole thrice. Right? Now, if this is the covalent character order, so what would be the order of ionic character? Just reverse of it. This is the order of ionic character. If this is the order of ionic character, what is going to be the order of solubility? Solubility is directly proportional to ionic character. So same is going to be the order of solubility as well. So FeOH whole thrice would be less soluble than that of FeOH whole twice. I hope I'm clear with this as well. Right? Okay. Now guys, there is one more application of this. What is that? That is your melting point. Melting point application. See, generally what do you observe? You observe melting points of ionic compounds. Generally would be greater than that of melting point of covalent compounds. melting point of ionic compounds would be generally more than that of melting point of covalent compound. Now, people, what does that mean? Simply tells me that if melting point of ionic compounds is more than that of melting point of covalent compounds, I would say melting point is nothing but it is directly proportional to ionic character, inversely proportional to the covalent character. Inversely proportional to the covalent character. Now you can easily solve this question. Now we can easily solve the questions. This is BeCl2, right? MgCl2, CaCl2, SrCl2, BaCl2. These are the chlorides of group second. These are the chlorides of group second. People, if I ask you down the group, say this is Cl negative, Be dye positive. This is Cl negative, Mg dye positive. Cl negative, calcium dye positive, right? So anion everywhere is same. Talk in terms of cation. On moving from top to the bottom, what happens to the size of cation? Size of cation increases. Lesser the size of cation, more the polarizing power of cation. More polarizing power of cation means more covalent character. So what is the order of covalent character here? BeCl2 has got maximum covalent character, followed by MgCl2, followed by CaCl2, followed by SrCl2, followed by BaCl2. This is the order of the covalent character. If this is the order of covalent character, so what do you think is going to be the order of ionic character? Ionic character order would be reverse. If this is the order of ionic character, what do you think is going to be the order of solubility? Same is going to be the order of solubility as well. Done and dusted. Right? Perfect. I believe this is clear. All right, people. Perfect. Now comes your one more concept, one more question, which is frequently asked. That's about the dipole moment. Okay, that's about the dipole moment. Now, first of all, what is a dipole? And what kind of questions do we get from the dipole moment? All of things I'll tell you in just 1 or 2 slides. Okay, all the things I'll tell you in just 1 or 2 slides. That's enough. And then we'll solve the questions. And by the way, the order which I gave you, your melting point, right? Your, what was the first one? Solubility and even thermal stability, that follows the same order. Right? Thermal stability of ionic compounds would be more than that of the covalent compounds. Or you can say thermal stability is directly proportional to ionic character, inversely proportional to covalent character. Right? So you can do that too. Anyways, I'm moving on to the dipole moment. See guys, what is first of all a dipole? What is a dipole? My dear students, whenever you have got equal and opposite charges, separated by some distance, this system of charges, the system of equal and opposite charges separated by certain distance. The system of equal and opposite charges separated by certain distance is what you call as a dipole. The system of equal and opposite charges separated by a certain distance is what you call as dipole. Let me tell you, for a dipole, we define a moment. We define its moment. For a dipole, we define its moment, mu. This dipole moment, it is first of all defined as, for the dipole, we define its moment like this: charge multiplied by distance. Charge multiplied by distance. It gives me what? It gives me the dipole moment, which is what? Which is a vector quantity. Right? Dipole moment. It's a vector quantity. And its direction in chemistry is taken from positive to negative. In chemistry, its direction is taken from positive to negative, or you can say from less electronegative element to more electronegative element. From less electronegative element to more electronegative element. For example, let's say people, we have got HCl molecule. This, for example, your HCl. If this is your HCl molecule, if I ask you among hydrogen and chlorine, which one is more electronegative? Among hydrogen and chlorine, I would say chlorine is more electronegative. If chlorine is more electronegative, chlorine will have delta negative charge, hydrogen will have delta positive charge. Do you see one thing? We got equal and opposite charges separated by certain distance. So this molecule is behaving like a dipole. And for the dipole, we define its moment. For dipole, we define its moment. And the direction of this moment will be from positive to negative, from less electronegative to more electronegative. This is the direction of the dipole moment for this molecule. Okay. This is the direction of dipole moment for this molecule. Perfect. I believe this is clear. Guys, let me tell you one more thing. Lone pair also contributes. Lone pair also contributes towards what? Towards the moment. Lone pair also contributes towards the moment, and its direction is always towards the lone pair. Its direction is always towards the lone pair. What does that mean? So yes, for example, this is your NH3 molecule. Let's say this is your NH3 molecule. Now, if you look carefully, there's a bond between nitrogen and hydrogen, right? So, nitrogen, hydrogen. Less electronegative to more electronegative. Less electronegative to more electronegative. Less electronegative to more electronegative. Now, nitrogen has got a lone pair as well. And lone pair also contributes to the moment. And the direction of moment due to lone pair is always towards the lone pair. So, due to lone pair, its direction is like this. Okay? So remember, lone pair also contributes towards the moment, and the direction is always towards the lone pair. This is one important point which you need to know. Perfect. Now guys, there are few more things which you need to know. After that, I'll show you a lot of questions based on dipole moment as well. See, that particular molecule whose net dipole moment is 0. That particular molecule whose net dipole moment is 0, you call that molecule as the non-polar molecule. And that molecule whose net dipole moment is non-zero, you'll be calling that as the polar molecule. You'll be calling that as the polar molecule. Okay. Now people, few types of the molecules I would want you guys to remember for now. AB2L0, AB3L0, AB4L0, AB5L0, AB6L0, AB7L0, AB4L2, AB2L3. These are the molecules which are always having the net dipole moment as 0. So these molecules would be always non-polar. So whenever a question is asked, which of the following molecule is non-polar? If there is any molecule belonging to this category, if there is any molecule belonging to this particular category, you'll be calling that directly as the non-polar molecule. Okay? Perfect. This is one of the important points which you need to know. Now, few more points I would want to discuss with you. After that, we can solve the questions. See, I told you, your dipole moment. Your dipole moment is nothing. It is the multiplication of charge and distance. So, I would say more the charge, more the dipole moment. When can be the charge on atoms same? I mean, when can be the charge on atoms more? Charge on atoms can be more when? When the electronegativity difference is more. When the electronegativity difference between the atoms is more. When the electronegativity difference between the atoms is more, I will say charge on the atoms is more. And if charge on the atoms is more, automatically I would say that dipole moment would be the more. Similarly, if the distance is more, if the distance between the atoms is more, again I can say, if the distance between the atoms is more, again I can say dipole moment is going to be more for that particular molecule. Okay? Perfect. Am I clear with this? Am I clear with this, guys? Perfect. Now, among NH3 and NF3, which one has got more dipole moment? What do you think? Among NH3 and NF3, which one has got more dipole moment? That's what I'm asking. Among NH3 and NF3, which one has got more dipole moment? See, guys, imagine this your NH3 here on one side, and this your NF3. This is your NF3. NH3 on one side, NF3 on the other side. Now, first of all, if you talk about this bond, moment is from less electronegative to more, less to more, less to more, less to more. Similarly, less to more electronegative, less to more electronegative, less to more electronegative towards the lone pair. Okay? In both the molecules, if you see the first one, do you see all the moments converging into one direction? All the moments are converging into one direction. So this is the net dipole moment, for example. Here, 3 moments are going downwards, 1 moment is going upwards. Can I say there will be some cancellation of the moments? These moments are basically the vectors. So some cancellation will happen over here, right? Here, no cancellation is happening. Here, some cancellation is happening, right? So where would be the net dipole moment more? I would say it's going to be NH3, which has got more net dipole moment than that of NF3. As simple as that. Correct? Now, similarly, guys, CCl, less electronegative to more electronegative, less to more. Both the moments are going in the same direction. So this is your net dipole moment. Less electronegative to more, less to more, equal and opposite moments. So net dipole moment of this particular molecule is 0. I would say first one has got more dipole moment than that of second one. Simple. HF, HCl, HBr, HI. More the electronegativity difference, more the electronegativity difference, more are the charge on the atoms, more the charge on the atoms. I would say more is going to be the dipole moment. Simple. Right? Perfect. Similarly, guys, there are a few more cases. This is a special case, CH3F, CH3Cl. It's a special case. Remember this. Okay. So if I talk about your CH3F and CH3Cl, here we have got a bond between C and F. Here we have got a bond between C and L. Right? As per charge factor is concerned, electronegativity difference here is more. If electronegativity difference here is more, so here there should be more dipole moment. So as per charge factor, dipole moment of 1 should be more than that of 2. As per charge factor, dipole moment of 1 should be more than that of dipole moment of second, because the electronegativity difference here is more, right? But as per the distance factor, CCl bond length is more. If CCl bond length is more, that means dipole moment of 2 should be greater than that of 1. And this is the case where distance dominates over charge. So I would say, in nutshell, the dipole moment of 2 would be greater than that of dipole moment of 1. So CH3Cl has got more dipole moment than that of CH3F. Remember this, guys. Okay? CH3Cl has got more dipole moment than that of CH3F. Rest all are same. CH3Br, and here you have got CH3I. This is the order. Okay? H2O, H2S. The bond is between oxygen hydrogen. The bond is between sulfur hydrogen. More the electronegativity difference, more are the charges on the atoms. More charge on the atoms means more is going to be the dipole moment. Here, more is the difference, more the difference. As simple as that. Guys, break I'll be giving you at 1:30. Okay? Just wait, we have got time. I hope this is clear. So first of all, whenever a question is asked about the dipole moment, the first factor which you'll be always saying, what is that? The first factor which you'll be always saying, that is going to be your charge. That's going to be basically your electronegativity difference. More the electronegativity difference, more the charge on the atoms, more the dipole moment. This is the case wherein you have to consider distance. Okay. All right. Look at these cases. You have to check the dipole moment again. You have to check the next dipole moment. You have to check the dipole moment again. See guys, CH3, is it electron donating or withdrawing? You know, your alkyl groups, they are donating groups. Electron donating groups. You should know it. Your alkyl groups, they are electron donating groups. So CH3, both are donating. If it is donating, so this will get positive, this will get negative. Right? It's donating, it's pushing electron density here. Similarly, donating. If this is donating, so I would say this will get positive, this will get negative. So you got two moments here, one moment from positive to negative, one moment here for positive to negative. Two moments opposite direction, so cancels out. So net here would be 0. Net dipole moment here would be 0. Okay, number 1. Now CH3 is donating, so positive to negative, positive to negative. So positive to negative in this direction, positive to negative in this particular direction. So one of the moment is going downwards, one moment is going in this particular direction. Angle between them, as you can see, will be 120 degree here. Angle between them would be 120. Similarly, this is positive to negative. This will be positive to negative. One going downwards, one going in this direction. This angle would be 60. This angle would be 60. Now, first of all, lesser the angle between the two vectors. Lesser the angle between the two vectors, more is going to be the resultant. So where is going to be the resultant dipole moment maximum? It's going to be maximum in third case, followed by 2, followed by 1. This is the order of the dipole moments here. Right? This is the order of the dipole moments here. Now, if you check the next case, this is no doubt electron donating, but this is withdrawing. NO2 is withdrawing group. If this is donating, if CH3 is donating means positive, negative. So positive, negative, positive to negative, because it's withdrawing, right? It's withdrawing. NO2 is withdrawing. It will drag the electron density towards NO2, right? So one is pointing downwards, one is going in this particular direction. Angle here is 120 degree, right? This is the direction of one, positive, negative, positive, negative. So one going in this direction, one going in this direction. Angle here is 60 degree. Positive, negative, positive, negative. Both the vectors here in the same direction. Angle here is 0 degree. Lesser the angle between two vectors, more is going to be the resultant between them. So resultant is maximum in third, followed by second, followed by first. So this is the order here. This is the order here, people. This is the order here. I believe this is clear. I believe this is clear. Okay. Now, our next topic is going to be the valence bond theory. But before starting valence bond theory, just let me know once in the chats if all the things till here are clear or not. Quickly. Let me know in the chats if all the things still here are clear or not. Everyone. Everyone. All the things are clear? Yes, next chapter is going to be periodic classification. Next chapter will be periodic classification. Break I'll give at 11:30. Sorry, break I'll give at 1:30. Okay. Remove on. NO2 is electron withdrawing group, right? That's something you study in GOC, electron withdrawing. Yes, only one exception is there in dipole, yes. Only one. Perfect. My dear students, when it comes to your valence bond theory, it explains the formation of covalent bond. Valence bond theory, it explains the formation of what? It explains the formation of covalent bond. This theory is going to let us know how a covalent bond exactly is formed. Okay, number one. Number two, as per this particular theory is concerned, a covalent bond between two atoms is formed by the overlap of atomic orbitals of bonding atoms. So, as per VBT is concerned, a covalent bond is formed only when the atomic orbitals of bonding atoms will overlap. What is overlap exactly? Overlap simply means penetration of atomic orbitals into each other. Penetration of atomic orbitals of bonding atoms into each other is what you call as overlapping. For example, let's say this is the atomic orbital which I'm representing of one bonding atom. This is the atomic orbital of one more bonding atom, right? Now, imagine they have to overlap. Overlap means their electron clouds will penetrate into each other. Their electron clouds will penetrate into each other, right? This is what you call as overlapping. And due to overlapping, which bond gets formed? Due to overlapping, as per VBT, covalent bond gets formed. Due to overlapping, I must say, covalent bond gets formed. Okay? Covalent bond gets formed. Now, guys, how this overlapping happens? What are the different types of overlappings? That's something which we have to discuss. As per your valence bond theory is concerned, valence bond theory, it explains the formation of covalent bond. Number one, valence bond theory says that atomic orbitals of the bonding atoms, they are going to overlap. They are going to penetrate into each other. And that penetration of atomic orbitals into each other is what you call as overlapping, right? And due to overlapping, which bond gets formed? Due to overlapping, covalent bond gets formed. Now, my dear students, this overlapping is actually of two types. One is called as axial overlapping. One is called as parallel overlapping. One is called as axial overlapping. One is called as parallel overlapping. If I talk about the axial overlapping, in case of axial overlapping, I would say atomic orbitals overlap. Atomic orbitals overlap along the axes. Atomic orbitals overlap along the axes. You call this axial overlap as the head-on overlap as well. You call this as the head-on overlap as well. And let me tell you, due to the axial overlap, which bond gets formed? Covalent bond. Which type of covalent bond? That's what you call a sigma bond. Due to axial overlap, sigma bond gets formed. Due to axial overlap, sigma bond gets formed. Similarly, in case of parallel overlap, what happens? I would say atomic orbitals overlap by keeping their axes parallel. Atomic orbitals overlap by keeping their axes parallel. What exactly it means, you'll get the idea in some time. Okay? And due to the parallel overlap, which bond gets formed? Covalent bond. And which covalent bond? You call that as the pi bond. So either pi bond gets formed or delta bond gets formed. Okay? Either pi bond gets formed or delta bond gets formed. Now we are going to understand both these overlaps in detail. One is your axial overlap, one is your parallel overlap. What happens in axial overlap? What happens in parallel overlap? Let's get to know about that. So my dear students, here I'm marking the heading as the axial overlap. Due to axial overlap, which bond gets formed? Sigma bond gets formed. Due to axial overlap, sigma bond gets formed. Okay. Now, the first type of the axial overlap is what I'll be calling as SS overlap. SS overlap. Try to understand what exactly I'll be talking about. Imagine, my dear students, s orbital of one atom and similarly s orbital of one more atom. S orbital of one atom, s orbital of one more atom. They are going to approach towards each other along this particular axis, which I'm calling as internuclear axis, right? Imagine this your z axis, right? Let's say these two s orbitals, they're approaching into each other, and when they approach into each other, when they approach towards each other, I would say their atomic orbitals will merge into each other. Their electron clouds will merge into each other, and this merging of electron clouds into each other is what you call as overlapping. And due to overlapping, what happens? Due to overlapping, a bond gets formed. Due to overlapping, covalent bond is formed. Which overlapping this is? This is overlapping along the axis. So which bond got formed here? I would say it is basically the sigma bond which would be getting formed here, right? And my dear students, later on what happens? This common electron density, it arranges itself. This common electron density, it arranges itself in such a way that it comes under the influence of both the nuclei. This common electron density arranges itself in such a way that it comes under the influence of both the nuclei. This common electron density, it arranges itself in such a way that it comes under the influence of both the nuclei. This is the common electron density which has come under the influence of both the nuclei, and I must say over here, which bond has formed? It is a sigma bond that has got formed. My dear students, basically in case of overlapping, overlapping happens in two ways. One is called as positive overlap. One is called as positive overlap. One is called as negative overlap. One is called as positive overlap. One is called as negative overlap. Positive overlap leads to the bond formation. Positive overlap leads to the bond formation. Negative overlap does not lead to the bond formation. And let me tell you, SS overlap is always positive. SS overlap is always positive. Okay, this was your SS overlap. Second is your SP overlap. Which overlap I'm talking about? I'm talking about axial overlap. SP, axial overlap, right? Let's say first of all, this is your internuclear axis. This is the internuclear axis, which is the Z axis, for example. Let's say this is the S orbital of one atom, and this is the P orbital of one more atom. Imagine this is PZ. If this is Z axis, so this has to be PZ. Perfect. Now, as I told you, overlapping can be of two types. One is called your positive overlap. One is called as the negative overlap. Let me show both. This is again the S orbital here. This is the P orbital here. Now, for example, I have to show both positive as well as negative. See, in order to show the positive overlap, let me, for example, keep positive here. Let me give the sign positive. Let me give the sign negative. In order to show the negative overlap here, let me give this a sign positive. Let me give this a sign negative. Let me give this a sign positive. My dear students, whenever I will have to show the positive overlap, at that point of time, I'll have to keep the same sign on same side. Same sign, same side means positive overlap. Same sign, same side means positive overlap. Opposite sign, same side means negative overlap. So here positive overlap will happen, right? So atomic orbitals will penetrate into each other, right? Which is what you call as overlapping. And due to overlapping, which bond gets formed? I would say here, it is a head-on overlapping. It is a direct overlapping. So I would say sigma bond will get formed here, right? In this particular case, if you see opposite signs on same side, opposite signs on same side means negative overlap, and negative overlap does not lead to the formation of the bond. Okay. So this was SS, axial overlap, SP, axial overlap. The third one here is PP, axial overlap. The third one here is PP, axial overlap. So how this PP axial overlap looks like? How this PP axial overlap looks like? My dear students, for example, this is your z-axis. For example, this is your z-axis, right? Let's say this is one of the p orbitals, and this one more p orbitals. I'm calling this as pz. I'm calling this as pz as well. I'm reiterating the same thing. Let me again make these orbitals here. Let's say this is your pz. Let's say this again your pz. Okay. Now, first of all, this is going to be the overlapping along the axis. Overlapping along the axis means axial overlapping. Axial overlapping leads to formation of sigma bonds. Now, let me give this as a positive sign, negative. Let me give this as a positive, negative. Do you see same sign on same side? Yes. Same sign, same side means positive overlap. So, what is going to happen? These atomic orbitals will merge into each other. These atomic orbitals will merge into each other, which is what I call as overlapping, right? And finally, this electron density will arrange itself in such a way that it comes under the influence of both the nuclei. So this is how it is going to come at the end, right? This is the plus sign here. This lobe has got negative. This lobe has got negative. And these two lobes have got positive over here. So which bond got formed here? I would say again a sigma bond got formed because it was the case of the head-on overlap, axial overlap. Now people, if you look here, let me give this as a positive, let me give this negative, let me give this negative, this positive. Opposite sign on same side, negative overlap, no bond formation, right? So this was all about your axial overlapping, which leads to the formation of what? Which leads to the formation of sigma bonds, right? Your axial overlapping, which leads to the formation of which bonds? Sigma bonds. All right. If you look at the parallel overlapping, let's see how the parallel overlapping looks like. Parallel overlap happens between the orbitals, right? I mean, orbitals will overlap by keeping their axes parallel. Orbitals will overlap by keeping their axes parallel. And due to parallel overlap, either pi bond gets formed or delta bond gets formed. Either pi bond gets formed or delta bond gets formed. See how exactly. See how exactly. The first type of the parallel overlap is your PP parallel overlap. The first type of overlap, the first type of parallel overlap is your PP parallel overlap. Now, what happens in PP parallel overlap? My dear students, imagine this to be your z-axis. If this is z, right, then this is going to be your py, for example. This is also going to be your py. This is also going to be your py. Let me give the signs as well. Positive, positive, negative, negative. Same sign, same side. So it's going to be the case of, which overlap? Positive overlap, right? Now, these atomic orbitals are overlapping. They are going to come closer with their axes parallel. Right? Okay? And when these atomic orbitals will come closer with their axes parallel, I would say their lobes will overlap. Their lobes will penetrate into each other. Into each other. And how do I get it at the end? See, this is how you are going to get it. Let's say this is one of the plane which I'm representing over here. This is one plane, right? This is one plane which I'm showing over here. It is one plane. Now, as you can see, above the plane and below the plane, you will find electron density here. So, electron density you are going to find above the plane and below the plane. Electron density you are finding above the plane and below the plane. So on this plane, there is no electron density. Electron density is present above the plane and below the plane. So on this plane, there is no electron density. That means no electron density means it contains a nodal plane. It is what I'll be calling as the nodal plane. Okay. So people, if you see, this was PP parallel overlap, due to which bond gets formed? Pi bond. And this pi bond which got formed here is what I call as p pi bond. Is what I call as p pi bond. Okay. Similarly, guys, if you look at it in this way, these are two orbitals parallel to each other. Now this is positive, this is negative, this is negative, this is positive. Lobes on same side. Same sign, or opposite sign? Opposite sign, same side. So negative overlap. Negative overlap means no bond formation. Negative overlap means no bond formation. So this was your PP overlap, which leads to the formation of pi bond, right? Like your P pi P pi. Second type of parallel overlap is what you call as PD overlap. PD overlap. PD parallel overlap, okay? PD parallel overlap. For example, this is your py orbital, and this is your, let's say this is your dxy, py and dxy. When they will come closer, let's say first of all this is positive, this is negative, positive, negative, positive, negative, negative, positive. Now, when they are going to overlap, what is the scenario? What is going to be the scenario here? This is going to be the scenario, right? Is this the case of head-on overlap or parallel overlap? This is the case of parallel overlap again, and parallel overlap leads to the formation of pi bond. Which pi bond got formed? I'll be calling this as p pi d pi bond, right? And over here, if you look, same sign on same side. So this is the parallel, this is the positive overlap. I could have shown the negative overlap as well by just interchanging the signs. That's something which I believe you know now. That's what I'm not going to show now. Then we have got DD parallel overlap. How this DD parallel overlap looks like? Let's say this is one of the d orbitals. Okay. Similarly, the same d orbital here, right? Let's say this was your dxy. Similarly, for example, this is your dxy, right? When they overlap, what's going to happen? I'm going to show the positive overlap. And if you want to show the positive overlap, you have to keep the same sign on same side. Positive, negative, right? Positive, negative. Same sign, same side. So, what is going to happen? These two lobes are going to overlap into each other. When they are going to overlap, this is how it looks like. This is how overlapping looks like here. And since a bond got formed, overlapping has taken place. Due to overlapping, which bond gets formed? Covalent bond. Which covalent bond? It's pi bond which gets formed. And which pi bond this is going to be? I'll be calling this as d pi bond. Even I'll be calling this as two-lobe interaction here. You can call this as two-lobe interaction. My dear students, there could have been the case of four-lobe interaction as well. Due to which delta bond gets formed. Due to which delta bond formation takes place. For example, if this is your one of the d orbitals, and here I'm representing one more d orbital. Let's say this d orbital is present on the board. Now this particular d orbital is coming on the top of it. If it is coming on the top of it, what is going to happen? I would say this lobe will interact with this lobe. This lobe will interact with this lobe. This particular one will interact with this one. And this one will interact with this one. So this is what I call as four-lobe interaction, and due to four-lobe interaction, which bond gets formed? It is the sigma bond, it's the delta bond which gets formed due to the four-lobe interaction. Okay? Perfect. All right, people. All right. Can you tell me one thing? S plus px. S plus px, keeping x-axis as the internuclear axis. S plus px, keeping x-axis as the internuclear axis, will form which bond? Is it sigma or pi or delta? What do you think? S plus px, keeping x-axis as the internuclear axis. What do you think? If x-axis is kept as the internuclear axis, then S and px will form which bond? It's going to form sigma bond, right? Now tell me, S plus Px, keeping y axis as the internuclear axis. Keeping y axis. Imagine this is your y axis. Imagine this is your y axis. This is S. So this has to be Px then, for example. So S plus Px. Will there be any overlap? It is a case of zero overlap. No bond. Right? There'll be no bond. Okay. Tell me one thing. For example, Px plus Px, keeping y-axis as the internuclear axis. Px and Px, keeping y-axis as the internuclear axis. What do you think? If I keep y-axis as the imagine this is your y-axis, right? This is Px, this is Px. So they'll show parallel overlap. So which bond gets formed here? I would say pi bond would get formed here. Okay, pi bond would get formed here. For example, Py and dxy, keeping x-axis as the internuclear axis. Which bond? Py and dxy, keeping x-axis as the internuclear axis. Which bond gets formed? Which bond gets formed here? Py and dxy, keeping x-axis as the internuclear axis. This is your x-axis, which I'm keeping as the internuclear axis. This is your Py, and this is your dxy. So which bond it's going to be? It's going to be p pi d pi bond. So it's pi bond. Pi bond would be getting formed here. I hope this is all clear. Right? I hope this is all clear. This was your overlapping, your VBT. I believe it's clear to everyone. Let me show you one of the molecule. Let me show you the formation of N2 molecule through VBT. Formation of N2 molecule through VBT. Let's have a look on this. How N2 molecule gets formed. See guys, this is your one of the nitrogen atoms. This one more nitrogen atoms. What is its outermost configuration? 2p3. Its outermost configuration is again 2p3, right? So this is your 2p carrying your 3 orbitals, 1, 2 and 3. This again your 2p carrying 3 orbitals, 3 electrons, right? Let's call this as px, let's call this as py, let's call this as pz. Let's call this as px, let's call this as py, let's call this as pz. Okay? So what's going to happen? Let's say this nitrogen atom I'm talking about, it has got 1 px. I'm calling this as px. Px carrying 1 electron, right? It has got py also. Let me call this as py carrying 1 electron. It has got pz also. Let me call this as pz carrying 1 electron. Talk about one more nitrogen. This nitrogen also has px, py, pz. So what will happen? Px will come from this side and will do the overlap. So this is the overlap, right? Now there is py as well carrying 1 electron. So this is, for example, your py carrying 1 electron. Similarly, there is pz carrying 1 electron. This is your pz carrying 1 electron. So over here, if you look carefully, what kind of overlapping this is? This is your head-on overlapping. So which bond gets formed? First, sigma bond. So sigma bond has got formed here, right? Now this is py, this is py. Both are parallel. If they are parallel, they'll show which overlap? They'll show parallel overlap. So these will show parallel overlap. Similarly, your pz and pz, they're also parallel. If they are parallel, so they are also going to show parallel overlap. So how many bonds got formed here? 3 bonds got formed. 1 is sigma and 2 is pi. 1 sigma and 2 pi. So this is n and n. 1 is sigma and 2 are pi. Okay. Remember one more thing. Sigma bond is stronger. Sigma bond is stronger than which bond? sigma bond is considered to be stronger than pi bond. Why? Because 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 strength of the bond is directly proportional to the extent of overlap. Strength of the bond is directly proportional to the extent of overlap. And let me tell you, extent of overlap in axial is more than that of extent of overlap in parallel. And if extent of overlap in axial is more than that of parallel, through axial overlapping sigma bond gets formed, through parallel overlapping pi bond gets formed. So if extent of overlap is more in axial, that means strength of the sigma bond would be definitely more than that of the strength of the pi bond. Okay? I believe I'm clear. Perfect, guys. All right, so this was your VBT and the formation of N2 molecule through VBT. Remember, sigma bond is stronger than pi bond. Why? Because strength of bond is directly proportional to extent of overlap. Overlapping happens more in axial than in parallel. And if I ask you which bond gets formed first, I would say it is the sigma bond that gets formed first, followed by the pi bond. Delta bonds are not in your syllabus basically. I just gave you the glimpse of what delta bond is. They won't ask you about the delta bonds. Don't worry about that. Okay? So next topic is hybridization, which we shall be discussing after the break. So I'm giving you the break till 2 p.m. I would want you guys to be back till 2 p.m. I'll start exactly at 2 p.m. guys, huh? I'll start exactly at 2 p.m. I'll start exactly at 2 p.m. So be back exactly on time, because now we are going to do something really amazing. That's going to be your hybridization. After that, there is VSEPR, followed by MOT, and done with this. So I would want you all to be back by 2 p.m. sharp. See you in a while. So are you guys back? Yes. Welcome back, guys. Welcome back. So, guys, now we are going to move into one more important topic. That is your hybridization, right? Have you studied this particular topic before? Just let me know once in the chats with a yes or no. Have you studied this particular topic before? Perfect, guys. So let's get going then. Let's see what this hybridization is all about. My dear students, first of all, let me teach you how to check the hybridization basically. How do we exactly check the hybridization? Then I'll show you how to apply the concepts of hybridization in the questions as well. Okay. So first of all, how do we calculate the hybridization? Let me first of all tell you, there is a method called as the steric number method. With the help of the steric number method, we can check the hybridization. My dear students, first of all, what this steric number exactly is all about? Let me tell you, this steric number is nothing but the number of sigma bonds with this, the number of sigma bonds which the central atom makes, the number of sigma bonds which the central atom makes, plus the number of lone pairs carried by the central atom. So sigma plus lone pairs, the number of sigma bonds that the central atom makes, plus the number of lone pairs which the central atom has. Okay, now have a look and remember a few things. You'll get all these things in some time. The first point, my dear students, remember, if the steric number comes out be 2, if the steric number value is equal to 2, at that point of time, the hybridization involved is SP. At that point of time, hybridization involved is SP. And let me tell you, the geometry which is predicted through hybridization, that is linear. That is linear. If steric number is equal to 3, the hybridization involved is sp2. The geometry predicted through hybridization is trigonal planar. Similarly, if the steric number is 4, hybridization involved is sp3. Geometry predicted through hybridization is your tetrahedral. It's tetrahedral. If steric number is 5, hybridization involved is sp3d. Geometry predicted through hybridization is trigonal bipyramidal. Similarly, if the steric number is equal to 6, hybridization involved is sp3d2. The geometry predicted through hybridization is octahedral. If the steric number is 7, hybridization involved is sp3d3. The geometry predicted through hybridization is pentagonal bipyramidal. pentagonal bipyramidal. These are first of all few things which I would want you guys to remember. Okay. Now guys, one more thing. Remember, in case of your sp3d hybridization, which orbitals participate in sp3d hybridization? It's going to be s, 3 of the p orbitals, px, py, pz, and which d orbital? It is dz square that participates in this hybridization. If you talk about your sp3d2 hybridization, which all orbitals participate in sp3d2? It is s plus px plus py plus pz, dx square minus y square, and dz square. These are the orbitals which participate in sp3d2 hybridization. In the similar way, which all orbitals participate in sp3d3 hybridization? It is going to be your s, px, py, pz, dx square minus y square, dz square, and dxy. These are the orbitals which participate in your sp3d3 hybridization. Okay. Now, my dear students, let's exactly get to know how this hybridization takes place in different molecules and how do we get to know their geometries. Try to understand what exactly I'll be doing. For example, I'm starting with BeCl2 molecule. One simple molecule I'm starting with, BeCl2. Try to understand what exactly I'll be doing. First of all, the central atom here is beryllium. The central atom here is beryllium. If I ask you, how many valence electrons beryllium has? Hydrogen, helium, lithium, beryllium. Beryllium has got 2 valence electrons. Understand the process which I'll be following. Beryllium has got 2 valence electrons. How many surrounding atoms this beryllium has? Beryllium has 2 surrounding atoms. That means 2 terminal atoms. Remember, the number of surrounding atoms gives you the number of sigma bonds. So that means your beryllium is forming 2 sigma bonds over here. Okay, your beryllium is forming 2 sigma bonds. Number of surrounding atoms is equal to number of sigma bonds. Now, my dear students, if beryllium had 2 valence electrons and it's forming 2 sigma bonds, so I would say both the valence electrons of beryllium, beryllium has used both these valence electrons to form the sigma bonds. I would say this beryllium, it had 2 valence electrons, and I would say it would have utilized both these valence electrons to form 2 sigma bonds. So, will there be any lone pair on beryllium? There will be no lone pair on beryllium. So, you got the sigma bonds, you got the lone pairs. What about the steric number? Steric number is sigma plus lone pair. Steric number is 2. And when the steric number is 2, hybridization involved is sp. So, in case of BeCl2, which hybridization is involved? It is your sp hybridization that is involved. So, what is going to be the geometry which is predicted through hybridization? It is going to be linear. It's going to be linear. Now, let me show it to you in detail as well, so that you can understand it properly. If I talk about beryllium, its configuration is 1s2, 2s2. 1s2, 2s2, and there is 2p as well, containing 0 electrons. Okay. Now, my dear students, look at this particular outermost configuration. Outermost configuration is 2s2 and 2p0. I would say this is the ground state electronic configuration of beryllium. This is the ground state electronic configuration of beryllium. So, if this is the ground state electronic configuration of beryllium, what would be the excited state electronic configuration of beryllium? Shift 1 electron here. When you shift 1 electron here, it is going to be like this. Okay, it's going to be like this. This is going to be the excited state electronic configuration of beryllium. Now, if I ask you which hybridization is involved, sp. So, I would say this s orbital of beryllium and this p orbital of beryllium, they would have intermixed. One of the s orbitals and one of the p orbitals of beryllium, they would have intermixed. And remember, number of atomic orbitals intermixing is equal to the number of hybrid orbitals formed. Number of atomic orbitals intermixing is equal to the number of hybrid orbitals formed. So I would say, my dear students, since s and p orbitals, they are intermixing, so there would be the formation of two hybrid orbitals, right? This particular hybrid orbital I'll be calling as sp hybrid orbital. Even this I'll be calling as sp hybrid orbital, right? So I got 2 sp hybridized orbitals. Now, my dear students, these hybrid orbitals containing electrons, they will arrange themselves in such a way they'll arrange themselves in such a way that there will be minimum repulsions between them. They'll arrange themselves in such a way, that there will be minimum repulsions between them. So this is how they have arranged themselves, right? Now, my dear students, after this, what is going to happen? Since this beryllium is forming bonds with chlorine, right? So I would say one of the chlorine atom will come from this side. One of the chlorine atoms will come from this side, and these chlorine atoms will start doing overlap with the hybrid orbitals of beryllium, right? Now, people, try to understand. If you talk about chlorine, chlorine's outermost configuration is 3p5. Chlorine's outermost configuration is 3p5. So 1, 2, 3, 4, 5. Let's call this as px. Let's call this as py. Let's call this as pz. So I would say this chlorine, this particular chlorine, I would say its unpaired orbital px will come from this side. This is the px orbital of beryllium, which has come from this side and done the overlapping. Similarly, the other chlorine, its px will also come from this side and will do the overlapping, right? And let me tell you, hybrid orbitals, they always lead to the formation of sigma bonds. When hybrid orbitals overlap, they lead to the formation of sigma bonds, except benzene. Okay? Now, people, try to understand. Is this the head-on overlapping? Yes, this is the head-on overlapping. So this is one sigma bond. This one more sigma bond. Okay? This sigma bond got formed between pure p orbital of chlorine and sp hybrid orbital of your beryllium. Even this got formed between pure p orbital of chlorine and sp hybrid orbital of beryllium. Perfect. And how do I represent it at the end? This is Be, and this is one sigma with Cl. This one more sigma with Cl. The bond angle here is going to be 180 degree, and the geometry is going to be linear. As simple as that. Okay, I believe this is clear to everyone. Okay? Is it? Is it, people? Let me show you one more case so that it becomes like very much clear to you. For example, if I take the case of CH4. It's again a simple molecule. Try to understand. In case of CH4, your central atom is your carbon, and carbon has got 4 valence electrons. How many surrounding atoms? 4. How many lone pairs on carbon? 0. Steric number is 4 plus 0, 4. Hybridization is sp3. Geometry predicted through hybridization is tetrahedral. Now, if you want to have a look on the actual structure, carbon, its outermost configuration is nothing but 2s2, 2p2. This is the ground state electronic configuration of carbon. Right? What about the excited state configuration of carbon? Excited state, I'll say one of the electron will go here, and when one electron goes here, this is the excited state configuration of carbon. Which hybridization is involved? sp3. So I would say one of the s and these 3p orbitals will intermix and will show sp3 hybridization. Since 4 atomic orbitals are intermixing, so they will lead to the formation of 4 hybrid orbitals. Okay? They lead to the formation of hybrid orbitals, 4. So this is, for example, one of the hybrid orbital. This is one more. This is one more. And this is one more. Perfect. Now, these hybrid orbitals containing electrons, they'll arrange themselves in such a way that there should be minimum repulsions and maximum stability. Right? Okay. So, people, now, how these 4 hybrid orbitals will arrange? This is one of the hybrid orbital. This is one more hybrid orbital. This is one more. And this is one more. So these are the 4 hybrid orbitals containing electrons. Now, my dear students, carbon is forming bonds with hydrogen. So I'll say one of the hydrogen will come from this side and will do the overlap. One more hydrogen from this side, one from this side, one from this side. Perfect. And due to which 4 sigma bonds get formed. This is CH, this is H, this is H, and this is one more H. So this is your CH4, which is sp3 hybridized, and its geometry is tetrahedral. And in case of tetrahedral geometry, what is the bond angle? 109 degree, 28 minutes. I hope this is clear to everyone. Okay. Now guys, this is something which you are not supposed to do in your exam. In exam, they'll give you the molecules. You have to talk about their hybridization or you have to talk about their geometry. Let me take some cases so that you can understand it. For example, I'm writing NH3. Let's say one more is for example XeF4. XeF4. For example, another one is XeF6. Let's say we have got one more as NO2 negative, right? Let's say we have got I3 negative. Let's say we have got I3 positive. I want to check the hybridization of each central atom over here. Now try to understand what do I do. Try to understand what do I do. See guys, first of all, your nitrogen is a central atom. How many valence electrons? 5. Surrounding atoms are 3. That means 3 sigma bonds. Out of 5 valence electrons, 3 are used. So nitrogen has got 2 electrons left as such in the form of one lone pair. So steric number is 3 plus 1, 4. So hybridization is going to be simply sp3. So geometry predicted through hybridization is going to be your tetrahedral. Yeah? XeF4, xenon. How many valence electrons xenon has? 8. How many sigma bonds it's forming? 4. Out of 8, 4 are used. So 4 will be left as such in the form of 2 lone pairs. So steric number is 4 plus 2, 6. Hybridization involved is nothing but sp3d2. Right? Similarly, XeF6. Xenon. How many valence electrons xenon has? 8. Out of 8, how many sigma bonds it's forming? 6. So there will be 2 electrons left as such in the form of one lone pair. So steric number is 6 plus 1, 7. Hybridization involved is going to be sp3d3. Okay. Now look at this particular case. NO2 negative. NO2 negative. Nitrogen. How many valence electrons it has? 5. But there is a negative charge. So add it up. So 5 plus 1, 6. How many surrounding atoms? 2 surrounding atoms means 2 sigma bonds. Right? Means 2 sigma bonds. Right? But if I ask you how many lone pairs nitrogen has? Nitrogen had 6 valence electrons. Right? It had 6 valence electrons. Right? Now, my dear students, oxygen is divalent. Oxygen is divalent. Perfect. If oxygen was not divalent, then what was I supposed to do? I was supposed to do 6 minus 2, 4. Then this nitrogen would have kept 4 electrons in the form of 2 lone pairs. But oxygen is divalent. Oxygen is divalent. So I'll assume one thing just for your convenience so that you can remember it. I'll assume as if this oxygen is forming, one oxygen is forming 2 bonds, one oxygen is forming two bonds with nitrogen. Let's assume that. Okay, just for your convenience so that you can remember it. See, out of 6 valence electrons, can I say 2 are utilized or 4 are utilized? I'll say 4 are utilized. So 2 electrons will be left as such on nitrogen in the form of one lone pair. So steric number is 2 plus 1, 3. Hybridization involved is going to be sp2. Okay, it's going to be sp2 hybridized. I hope this is also clear. You have got I3 negative. Now, if you talk about this I3 negative, I can write as I2 negative. Yes, I can do that. I3 negative, I can write as I2 negative. Now, my dear students, look at this particular iodine, which is a central atom. 7 valence electrons. There is a negative charge, so 7 plus 1 makes it 8. How many surrounding atoms? 2. So sigma is equal to 2. Out of 8 valence electrons, 2 are utilized. So it will have 6 electrons left as such in the form of 3 lone pairs. So how many lone pairs are here? 3. Steric number is equal to 3 plus 2, 5. So hybridization involved is going to be sp3d. Simple. Right? Talk about I3 positive. My dear students, this I3 positive I can write as I2 positive. Look at this iodine. How many valence electrons it has normally? 7. There is a positive charge, so subtract this. So 7 minus 1 makes it 6. How many surrounding atoms? 2. So there will be 2 sigma bonds. Out of 6 valence electrons, 2 are used. So 4 will be left as such in the form of 2 lone pairs. So lone pairs are 2. Steric number is equal to 2 plus 2, 4. If steric number is equal to 4, hybridization involved has to be sp3. Simple. So this is how you check, you predict the hybridization from which a direct question will be asked. Okay? A direct question will be asked from hybridization. Am I clear with this? Am I clear with this? Am I clear with this? Lavari, in case of coordination compounds, you have to check the ligands basically, whether there are strong field ligands attached, weak field ligands. Accordingly, you do the pairing, right? Then only you get to know what is the hybridization. And once you get the hybridization, then you can talk about the geometry as well. Okay. So my dear students, this was all about hybridization, and from hybridization, this direct questions will be asked. Nothing apart from this. Okay. Whatever things I was doing here, this is something which is not asked, right? This is for your understanding purpose, nothing more than that. Okay. All right. Can you give this a try? Can you tell me what is going to be the hybridization of nitrogen and NO2 positive? Can you tell me in the chats quickly? I'm waiting for your answers. I'm waiting for your answers quickly. What do you think? NO2 positive. What is the hybridization of nitrogen here? I want everyone to answer this. Amazing. That's great. See, nitrogen, how many valence electrons it has? 5. But there is positive charge, so subtract 1. So 5 minus 1 makes it 4. How many sigma bonds? 2. Now, oxygen is divalent. Oxygen is divalent. So you'll consider oxygen making 2 bonds. One oxygen making 2 bonds. So out of 4 valence electrons, how many are utilized? 2 or 4? 4 are utilized. So no lone pair on nitrogen. So steric number is equal to 2 plus 0, 2. Hybridization involved is sp. Hybridization involved is sp. I hope this is clear. Okay, amazing. Now, my dear students, the next thing which I'll be discussing with you, what is that? That is going to be your valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. Now, people, here, what kind of information this valence shell electron pair repulsion theory gives us? Let me first of all tell you that this VSEPR theory, it gives us the idea about the actual shape of the molecule. It gives us the idea about the actual shape of the molecule. What is the basis of this valence shell electron pair repulsion theory? See, for example, if I have NH3, let's say I've got NH3. This is your NH3, and these are the 2 electrons left as such on nitrogen. First of all, if I ask you, in nitrogen, there are 5 valence electrons. You know it. In nitrogen, there are 5 valence electrons. Out of 5, these 3 electrons have been used in bonding. So these electrons I'll be calling as bonding electrons. Bonding electrons. Well, these 2 electrons, they belong to the valence shell of nitrogen, but do not participate in bonding. So you call them as non-bonding electrons or lone pairs. You call them as non-bonding electrons or lone pairs. Well, bonding plus non-bonding, bonding plus non-bonding makes it, I'll be calling them as valence shell electrons. Bonding electrons as well as non-bonding electrons, I'll be calling them as the valence electrons of nitrogen. Okay. Now, people, as per your VSEPR theory is concerned, molecule tries to acquire that particular shape. I'll write it for you. Molecule tries to acquire that shape in which the repulsions between the valence shell electron pairs are minimized. Molecule tries to acquire that particular shape in which the repulsions between the valence shell electron pairs are minimized. First of all, let me tell you what is the order of the repulsions. Let me tell you, lone pair repulsions are maximum, followed by your lone pair bond pair repulsions, followed by your bond pair repulsions. Molecule always try to acquire that particular shape in which the repulsions between the valence shell electron pairs are minimized. And once repulsions are minimized, that means stability is maximized. Now, my dear students, one more thing. That molecule in which central atom does not have any lone pair. That molecule for which central atom does not have any lone pair. That molecule in which central atom does not have any lone pair. In that particular molecule, the geometry which is predicted through hybridization, is basically the actual shape of the molecule. That molecule in which the central atom does not carry any lone pair. In that particular molecule, whatever is going to be the geometry predicted through hybridization, that is going to be the shape of the molecule. Now let's have the detailed analysis of all this over here. My dear students, the first case which I am taking here, I am taking those molecules which have got steric number 3. If steric number is 3, yes, J aspirants can also watch it. If steric number is 3, hybridization involved is sp2. Geometry predicted through hybridization is trigonal planar. This is our first case here. Now people, if I ask you, how many possibilities are there to have the steric number 3? The first possibility is, if there are 3 sigma bonds, central atom is forming and there is no lone pair on central atom. This is first possibility. To have the steric number 3, 3 plus 0 as 3. Steric number is sigma plus lone pair. This is the first possibility. Second possibility is, if central atom is forming 2 sigma bonds and there is 1 lone pair on the central atom. This is second possibility. Whenever you see this type of the molecule wherein central atom has formed 3 sigma bonds and there is no lone pair on the central atom, you will say the type of the molecule as AB3L0, where A is the central atom, it is forming 3 sigma bonds, there is no lone pair on the central atom, so AB3L0. What is going to be the type of this molecule? You'll be writing it like this: AB2L1. A is the central atom, 2 sigma bonds, 1 lone pair on the central atom. Okay, number 1. Now, in this particular case, since the central atom does not have any lone pair, and when central atom does not have any lone pair, geometry predicted through hybridization is the actual shape. So I would say, in this particular case, your shape is nothing but, it is geometry which is predicted through hybridization, that is trigonal planar. Right? That is trigonal planar. And how do you exactly show it? This is A, this is B, this is B, and this is B. This is your trigonal planar geometry. If I ask you what is the bond angle here? Bond angle here would be 120 degree. I believe I'm clear with this. Similarly, 2 sigma bonds, 1 lone pair, AB2L1. Right? AB2L1. Steric number is 2 plus 1, 3. Hybridization is again sp2 only. Well, hybridization, you know, it's sp2. What is the geometry predicted through hybridization? I'll first of all say, geometry which is predicted through hybridization is trigonal planar. But what about the actual shape? How do you get the actual shape here in this particular case? My dear students, one thing you have to understand. First of all, in order to make the actual shape, make its geometry. What is geometry? That's trigonal planar. Trigonal planar was like this. But in this particular molecule, there are 3 sigma bonds. But do we need 3 sigma bonds or 2? We just need 2 sigma bonds. So I'll be removing one of the sigma bond, and instead of that, I'll be placing a lone pair. Right? Now hide this lone pair. How it looks like? It looks like bent. So its actual shape is bent. It is bent shaped. It is bent shaped. Okay. This was the first case, steric number 3. Similarly, if I talk about the second case, those molecules which have got steric number 4. Steric number 4 means hybridization is sp3. Geometry which is predicted through hybridization is tetrahedral. Is tetrahedral. Okay. Now, if I ask you what are the possible cases to have the steric number 4, what are the possible cases? The first case is if there are 4 sigma bonds and there is 0 lone pair. Second case is if there are 3 sigma bonds, there is 1 lone pair. Next case is if there are 2 sigma bonds and 2 lone pairs. Okay. First of all, what is the type of the first molecule? Type of the first molecule would be AB4L0. This would be AB3L1. This would be AB2L2. Okay. Here the central atom does not have any lone pair. So geometry predicted through hybridization is going to be the actual shape. So shape of this molecule is going to be tetrahedral. It is going to be tetrahedral. So for example, this is A, this is B, this is one more B, this one more B, and this one more B. So how does it look like? It looks like a tetrahedron. And here the bond angle is going to be 109 degree, 28 minutes. Okay. Right? I believe this is clear. Now similarly, AB3L1, central atom has the lone pair. Okay. So what about the shape now? What about the actual shape now? In order to make the actual shape, what do? We make the geometry first of all. What is the geometry? Tetrahedral. Tetrahedral was like this, AB4L0. This was the tetrahedral geometry. Now, do we need 4 sigma bonds or just 3 sigma bonds? We just need 3 sigma bonds. So, remove one and instead of this, put a lone pair here. Okay. So, how does it look like? It looks like pyramidal. So, its actual shape is pyramidal. Its actual shape is pyramidal. Similarly, AB2L2. Make its shape. For shape, what do we need? We need to make its geometry. Geometry is tetrahedral. Tetrahedral means it was AB4 this way. This was the tetrahedral geometry. Now do one thing. Remove 2 bond pairs and place 2 lone pairs. Let's say this one of the lone pair. This one of the lone pair. This also your bent shape, angular shape. Right? So in case of AB2L2 molecule, the shape is bent. I believe I'm clear. Okay. Now, similarly, the third case, that is steric number 5. Third case is your steric number 5. Steric number 5 means hybridization involved is sp3d. Geometry predicted through hybridization is trigonal bipyramidal. It is trigonal bipyramidal, right? So what do I do here? In case of your sp3d geometry. In case of your sp3d geometry, I mean, what are all possibilities? What possibilities do we have to have the steric number 5? So first of all, the first possibility is all the 5 would be sigma bonds, 0 lone pairs. So 5 plus 0 is 5, first possibility. 4 lone pair 1, second possibility. 3 lone pairs 2, right? Third possibility. Sigma 2 lone pairs 3, next possibility. These are different possibilities to have the steric number 5. Now, my dear students, what is the type of the first molecule? It's going to be AB5L0. This is going to be AB4L1. This is your AB3L2. This is going to be AB2L3. AB2L3, right? Perfect. Now, my dear students, in case of AB5L0, since central atom does not have a lone pair, when the central atom does not have a lone pair, geometry predicted through hybridization is going to be the shape. So if I ask you what about the actual shape of the molecule, you'll say shape of the molecule is going to be same, trigonal bipyramidal. Perfect. And this how it looks like. This A, B, B, and B. These are what I call as equatorial bonds. All these 3 bonds, they are present on the same plane. Imagine they are present on board, one perpendicular to board towards me, one perpendicular to board away from it. Okay, away from it. Right? So how it looks like exactly? This is your equatorial plane. So this is your trigonal bipyramidal shape here. Perfect. I hope this is clear. Well, this bond, and this bond, what do you call them as? Equatorial bonds. This particular bond and this particular bond, you call them as the axial bonds. You call them as the axial bonds. Okay. And remember one thing, axial bond length, in case of trigonal bipyramidal geometry, axial bond length would be greater than that of equatorial bond length. Axial bond length would be greater than that of equatorial bond length in case of sp3d geometry. Now, AB4L1. AB4L1. What is going to be its shape? What is going to be its shape? It's seesaw shaped. It's seesaw shaped. Okay. So how it finally looks like? This is A. This is B. This is B. And here at the equatorial position, I'm keeping a lone pair. One perpendicular be upwards, one downwards. So this is your seesaw shaped structure. Similarly, AB3L2. 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 In case of AB3L2, what is going to be the shape? Shape is going to be T-shaped. It's a T-shaped molecule. How it looks like? Let me make it over here. This is A. One of the lone pair at equatorial. This is axial. This is axial. Hide these lone pairs. How it looks like? It looks like T-shaped. AB to L3. Its shape is going to be linear. AB to L3, its shape is going to be linear. How it looks like finally? This, for example, A, one lone pair at equatorial, one more, right? This is B here and this is B here. If you hide the lone pairs, the shape is going to be linear over here. Perfect. So they can be directly asked in your exam. They can be directly asked in your exam. I hope I'm clear with this. Yeah? I hope I am clear with this. So this was steric number 5. Now let's have a look on steric number 6 molecules. Steric number 6 means hybridization is sp3d2. Geometry is octahedral. Geometry predicted through hybridization is octahedral. Now, what are the different possibilities to have the steric number 6? What are the different possibilities? What are the different possibilities to have the steric number 6? See guys, the first possibility is if there are 6 bonds and 0 lone pair, right? I'm sorry. Second possibility is if there are 5 sigma bonds, 1 lone pair. Third possibility, 4 sigma bonds, 2 lone pairs. Check about the type of the molecule. Type of this molecule is AB6L0. Type of this molecule is AB5L1. Type of this molecule is AB4L2. These are the types of the molecules. These are the types of the molecules. Now, first of all, if I ask you about the shape of this molecule, since the central atom does not have a lone pair, and I have told you already, when the central atom does not have the lone pair, and the central atom does not have the lone pair, at that point of time, shape is going to be exactly the same, as that of geometry, which is predicted through hybridization. So what is the geometry predicted through hybridization? That's octahedral. So shape here is going to be octahedral too. So how it looks like this AB6L0 molecule, this A, this is B for example, this is B, one more B and one more B. So all these atoms, they are present on the same plane. They're present on the same plane. Now perpendicular to the plane, there is one B, perpendicular downwards, there is one more B. So what do you call this particular structure as? You call this as the octahedral shape, right? Perfect. Now, AB5L1. AB5L1. What about its shape? Its shape. In order to make its shape, what do we need to make first? The geometry. Geometry already you know, that's octahedral like this, AB6L0 type. This is the geometry. But in this geometry, there are 6 sigma bonds. How many I need? I need 5 sigma bonds. So I'll be removing one of the sigma bond, and instead of that, I'll be keeping a lone pair here. Perfect. Now hide the lone pair. See how it looks like. It looks like a square pyramid. It looks like a square pyramid. So its shape is square pyramidal. Its shape is square pyramidal. Okay. Now similarly, AB4L2 type. If you look at AB4L2 type, let me show it directly now. It is going to be square planar. Its shape is going to be square planar. Right? And how it looks like finally? This is A, this is B. Okay? One lone pair here, one more lone pair here. So this is your square planar shape in case of your AB4L2 type. I hope this is clear. Yeah? Is all this clear? Is all this clear? Yes, there is a lot more theory behind that. Let's ignore that. That's not needed. Okay. Perfect. Now I'll move on to one more important topic of this particular chapter. What is that? That's your MOT. That's your molecular orbital theory. That's your molecular orbital theory. Let me tell you, from the molecular orbital theory, questions are directly asked about the bond order, bond length, bond strength, right? All these types of the questions can be framed. Basically, many questions can be framed from the molecular orbital theory. But from this, in your NEET examination, they'll be only asking about your bond order, bond length, bond strength, etc., etc. How do we exactly do that? How do we exactly do that? See, guys. First of all, this molecular orbital theory, it is the extension of your valence bond theory. It is the extension of your valence bond theory. If you remember, as per your valence bond theory is concerned, valence bond theory said that atomic orbitals of the bonding atoms, they overlap. They overlap. Atomic orbitals of the bonding atoms, they overlap. Perfect. Now, molecular orbital theory is going to say the similar thing. As per molecular orbital theory, atomic orbitals, they combine. Atomic orbitals, they combine to form the molecular orbitals. Atomic orbitals of the bonding atoms, they are going to combine. They are going to lead to the formation of what? They are going to lead to the formation of molecular orbital, right? Next point, number of atomic orbitals combined. Number of atomic orbitals combined is equal to the number of molecular orbitals formed. Number of molecular orbitals formed. As per your MOT is concerned, again I'm telling you, it is the extension of your VBT. It is the extension of your VBT. Atomic orbitals combine to form molecular orbitals. Atomic orbitals of the bonding atoms, they are going to combine and they are going to lead to the formation of what? They are going to lead to the formation of your molecular orbitals. Number of atomic orbitals which combine is always equal to the number of molecular orbitals formed. For example, if two atomic orbitals are combined, let's say two atomic orbitals of bonding atoms are combining, they will lead to the formation of two molecular orbitals. They will lead to the formation of two molecular orbitals. One would be called as bonding molecular orbital. One would be called as anti-bonding molecular orbital. Let me tell you, energy of bonding molecular orbital is less and I would say its stability is more, right? Similarly, energy of anti-bonding molecular orbital is more and its stability will be less. Its stability would be less, right? For example, let's say this is the s orbital of one bonding atom. This is the s orbital of one more bonding atom. Okay. Let's say these atomic orbitals are combining. If these atomic orbitals will be combining, they will lead to the formation of two molecular orbitals. One would be called as bonding, one would be called as anti-bonding. Right? Now, SS is always head-on, and during head-on, which bond forms? Sigma. So I'll be calling this particular molecular orbital as sigma. Let's say this is your 1s, this is also 1s. So let me call this as sigma 1s, and this I'll be calling as sigma star 1s. This I'll be calling as sigma star 1s. Okay. Similarly, guys, for example, this is the p orbital of one bonding atom, p orbital of one more bonding atom. Let's say this is the internuclear axis. Perfect. Now, if two atomic orbitals are combining, they'll lead to the formation of two molecular orbitals. One would be called as similarly bonding. One would be called as anti-bonding molecular orbital. Right? Is this the head-on overlap here? Yes, it's the head-on overlap, due to which sigma bond gets formed. Let's say this was your 2pz. This was, for example, your 2pz. So I'll be calling this as sigma 2pz. This I'll be calling as sigma star 2pz. This I'll be calling as sigma star 2pz. Okay. Similarly, guys, for example, let's say this is your 2py. This is 2py. Let's say these atomic orbitals have to combine now. When they'll be combining, they'll be forming two molecular orbitals, out of which one will be bonding, one will be anti-bonding. Now, should I be calling them as sigma 2py or pi 2py? Should I be calling this as sigma 2py or pi 2py? This molecular orbital will be called as pi 2py, and this would be called as pi star 2py. So one thing which you need to remember, guys, molecular atomic orbitals of bonding atoms, they combine, they lead to the formation of molecular orbitals, out of which some are going to be bonding, some are going to be anti-bonding. And the number of atomic orbitals combined is equal to the number of molecular orbitals formed. Okay? Right, people? I hope it's clear till here. Now comes the point. Now comes the point. Since when these atomic orbitals combine, they lead to the formation of molecular orbitals. Once these molecular orbitals are formed, we are going to arrange the electrons in these molecular orbitals. We are going to arrange the electrons in these molecular orbitals as per your Abba's principle, as per your Hund's rule, as per your Pauli's exclusion principle, right? All those principles are taken into consideration while filling the electrons in these molecular orbitals. Now, first of all, you should know what is the electron filling order, which we are going to follow. What is the electron filling order which we are going to follow? This is the electron filling order, my dear students. This is the electron filling order which we shall be following up to the species containing total 14 electrons. Up to species containing 14 electrons. So that means first sigma 1s will be filled. Sigma 1s is going to be filled first, followed by sigma star 1s, followed by sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz. Similarly, pi 2p, pi star 2p, and sigma 2pz. Okay. So my dear students, again I'm telling you, we are going to fill the electrons in the molecular orbital as per this particular order, right? But this order is valid for those species which have got total electrons less or equal to 14, which have got total electrons less or equal to 14. Now here comes a point. Here comes a point. Understand properly what I'll be saying. Understand properly what I'll be saying. My dear students, with the help of MOT, with the help of molecular orbital theory, what can we do? We can calculate a term called as bond order. we can calculate a term called as bond order. What is bond order? Bond order simply gives you the number of bonds between two atoms. For example, you have got O2 molecule. Let's say you have got O2 molecule. You already know its structure. This is O double bond O. So there are two bonds present. So bond order is 2. N2 molecule. All of you must be knowing it's a triple bond. N triple bond N. So bond order here is 3. Right? H2 molecule. H2 molecule. You know its structure already. The bond order has to be 1. Now, I'm going to give you one formula with the help of which you can calculate bond order of any species. You can calculate bond order of any species. Bond order is nothing but it is half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. Half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. And remember, if bond order is 1, it represents the single bond between two atoms. Bond order 2 represents double bond. Bond order 3 represents triple bond. If bond order is less or equal to 0, that means that molecule does not exist. It is a non-viable molecule. That means that molecule does not exist. It is the non-viable molecule. That particular molecule in which bond order will be less or equal to 0. That molecule does not exist. It is non-viable in nature. Okay. Now let's see its application. Let's see its application. But before checking its application, there are a few more points which I would want you guys to remember. My dear students, bond order means number of bonds between two atoms. Can I say that will be inversely proportional to bond length? More the bond order. That means more are the bonds between the two atoms. More bonds means more attraction. More attraction means closer will be the atoms. Closer the atoms means lesser the bond length. Right? More the bond order means more is going to be the bond strength. More the bond order means more is going to be the bond strength. More the bond strength means more is going to be the bond dissociation energy. So anything can be asked out of these things. Anything can be asked out of these things. Okay, anything can be asked out of these things. I hope this is clear. I hope this is clear. Now people, understand one more thing. Understand one more thing. If you have got two species which have got same bond order. Imagine you have got two species which have got same bond order. Two species having same bond order. How do we check which species is more stable, which species is less stable? Normally, what do we see? More the bond order, more the stability. Normally, what do we see? More the bond order, more the stability. But if bond order is same, how do we check the stability? We check the stability with the help of antibonding electrons. More antibonding electrons means less stability. Less antibonding electrons means more stability. Remember this particular point as well. It will be used after some time. Okay, if the bond order is same, more the antibonding electrons, lesser the stability, lesser the antibonding electrons, more the stability. Now, let's utilize all of this in the questions. Let's utilize all of this in the questions. We have got H2 molecule. We have got H2 molecule. In H2, how many electrons will be there? Tell me that. How many electrons will be there in H2? In one hydrogen atom, there will be one electron. In a one hydrogen atom, there will be one electron. So in two hydrogen atoms, there will be two electrons. There will be two electrons, right? So I'll say both these electrons will go here. So its configuration becomes sigma 1s2. So if I want to calculate the bond order, how exactly I'll be doing it? Half of number of electrons in bonding. This is bonding, right? Minus number of electrons in anti-bonding. There are no electrons in anti-bonding, right? The value comes out to be 1. Perfect. Well, do you see any unpaired orbital here? It is paired. It's filled, completely filled, right? There are no unpaired electrons. No unpaired electrons means it's diamagnetic. No unpaired electrons means it is diamagnetic. No unpaired electron means it's diamagnetic. You have got He2. One helium atom has got 2 electrons. So 2 helium atoms will have 4 electrons. So fill these 4 electrons. 2 here and 2 here. So configuration becomes sigma 1s2, sigma star 1s2. This is the configuration. Now, if I want to calculate the bond order, half of number of electrons in bonding. How many electrons are in bonding? See, star means anti-bonding. Without star means bonding. How many electrons are in bonding? 2. How many electrons are anti-bonding? In anti-bonding, again 2. So the value comes out to be 0. And bond order 0 means molecule does not exist. Molecule does not exist. Let's say you have got Li2, 6 electrons in total. One lithium atom carries 3 electrons. Hydrogen, helium, lithium. Okay. So 2 lithium atoms carry 6 electrons. So fill these 6 electrons. 2, 4, 5 and 6. Okay. So configuration becomes sigma 1s2, sigma star 1s2, sigma 2s2. Correct? So calculate the bond order now. It is half of number of electrons in bonding, 2 plus 2, 4, minus number of electrons in anti-bonding. Anti-bonding is 2, 4 minus 2, 2 by 2 is 1. So bond order is 1. If bond order is 1, that means between 2 lithium atoms there is a single bond. Right? Do you see any unpaired electron here? This is S carrying 2, S carrying 2, S carrying 2. There is no unpaired. If there are no unpaired electrons, that means this particular species also is diamagnetic. There are no unpaired electrons. Yeah? What about the next one? Be2. One beryllium atom carries 4 electrons. So 2 will carry 4, 4, 8. Right? So 2, 4, 6 and this is going to be 8. So bonding 4, anti-bonding 4, 4 minus 4 by 2, that is 0. So bond order here is 0. So this molecule also does not exist. I believe I'm clear with this. This molecule also does not exist. Similarly, you have got B2. B2 means one boron has got 5 electrons. So 2 boron has got 10 electrons. So 2 here, 2 here, 2 here, 2 here. 2, 4, 6, 8. Now, these are degenerate. They have got same energy. And in degenerate orbitals, what do we do? What do we do in degenerate? Guys, just a second. What did I make here? This is orbital. Wait. What did I do? Oops. It's a mistake. This is pi 2p x orbital. This is pi 2p y. Sigma 2p z. Right? These are orbitals. I was considering them as the subshells. Wow. Okay. Okay, have a look. So first of all, 8 electrons we have filled till here. How many we have to fill? We have to fill 10. 8 we have filled. How many we have to fill? We have to fill 10. So 8 we have filled. These are degenerate. Their energy is same. So pairing won't happen. If one electron is shifted, if one electron I'll put here, then one more I'm not going to put here. I'll keep one electron here, because pairing in these orbitals, pairing won't happen unless each degenerate orbital gets one electron each. Okay, pairing won't happen. Pairing won't happen unless each orbital gets one electron each. Right? Perfect. Now you can calculate the bond order easily. Believe you can do that. So calculate the bond order. It's going to be equal to half of number of electrons in bonding. 2, 4, 5, 6. Minus number of electrons in anti-bonding. 4. So 6 minus 4 is 4. 4 by 2 is 2. So bond order is 2. If bond order is 2, that means there is going to be, if bond order is 2, that means there is going to be a double bond over here. Right? Okay. Wait, I don't know. What am I thinking? 6 minus 4 is 2. 2 by 2 is 1. Okay. So that means there is a single bond between boron and boron. Now tell me one more thing. In this particular configuration, do you see unpaired electrons? Yes, here we have got unpaired electrons. 2 unpaired electrons. Unpaired electrons means this particular species is going to be paramagnetic in nature. And its magnetic moment is going to be equal to under root of n into n plus 2 Bohr magnetrons, where n represents number of unpaired electrons. How many unpaired electrons do we have? 2. So it's going to be root of 2 into 2 plus 2. So 2 plus 2 is 4, 4 to 8. So root of 8 Bohr magnetron is going to be its magnetic moment as well. Yeah. Okay. Moving on to C2. In case of C2, how many you have? It's a 12 electron species. Perfect. If it is a 12 electron species, you can easily calculate its bond order, right? You can easily calculate its bond order. So till now we have filled 10 electrons. Now 11, 12. Perfect. 11, 12. Now guys, you can easily do bond order is equal to half of number of electrons in bonding 2, 4, 6, 8 minus number of electrons in anti-bonding 2, 4, 8 minus 4 is 4, 4 by 4 is 2. So in case of your C2 molecule, there's a double bond. And let me tell you, this is a special case here. In case of C2 molecule, normally what do you observe? Normally you observe one of the bond will be sigma, one of the bond will be pi. But remember, in case of your C2 molecule, both these bonds are pi bonds. So there are two pi bonds present here. Both these bonds are pi bonds in case of C2 molecule. Okay. Now at the same time, do you see any orbital unpaired here? There is no orbital unpaired. If there is no unpaired orbital, that means the species is going to be diamagnetic in nature. So this is diamagnetic. This is diamagnetic. Okay. Perfect, guys. So I believe all these things you can do easily now. You must be thinking N2 positive, since it has got 13 electrons only. Sorry, not N2 positive. You must be thinking N2 negative. N2 negative has got 15 electrons. But I'm telling you to follow this particular series up to 14 electrons. Then why have I kept N2 negative here? Why have I kept N2 negative here? My dear students, remember, N2 negative got generated from N2. N2 negative got generated from N2. And N2 has got 14 electrons. This is the parent species. This is the parent species. Whatever configuration parent species follows, the derived species are going to follow the same order. Okay? Remember this particular point as well. Whatever order the parent species follows, the derived species are going to follow the same order. Got it? Now, for example, here you have got N2 positive. Here you have got N2. You have got N2 positive. You have got N2 negative. When you calculate their bond orders, this bond order will be 3. N2 positive is the 13 electron species, so it's going to be 2.5. N2 negative bond order will be also 2.5 when you calculate it. Okay. So these are the bond orders. Now, first of all, which one has got the maximum bond order? Maximum bond order has got for N2. So if I ask you about the stability order, N2 is going to be maximum stable because its bond order is maximum. Now, among these two, bond order is same. Now, how do you compare the stability? Check the antibonding electrons. Lesser the antibonding electrons, more the stability. N2 positive has got lesser antibonding electrons, so it will be more stable than that of N2 negative. Okay, remember this particular stuff as well. Similarly, this is the electron filling order for more than 14 electrons. This is the electron filling order for more than 14 electrons, and you can do the similar way, right? Or guys, at the end, you can just remember one trick. One trick you can remember for the bond order calculation. Remember, whenever you have got a 14 electron species always will be having the bond order of 3. If you have got the 15 electron species, its bond order reduced by 0.5, so it's 2.5. 16 electron species, bond order reduced by 0.5 again, so it's 2. 17 electron species, bond order 1.5. 18 electron species, bond order 1. Similarly, 13 electron species, bond order is again going to be 2.5, reduced by 0.5, 0.5. 12 electron species, bond order 2. 11 electron species, bond order 1.5. 10 electron species, bond order 1. Okay? Remember this particular data. Okay? There is one more point from which question comes. What is that exactly? Fahim, see, if the question is directly asked about the bond order, then you can use the trick. But what if they ask you to calculate the magnetic moment, right? To calculate the magnetic moment, then you have to check in the configuration how many unpaired electrons are there. Once you get the unpaired electrons, then after that, you have to use the formula root of n into n plus 2. So for that purpose, you have to. right? All right, one more thing. My dear students, there is something called as isoelectronic species. Do you know what are isoelectronic species? Isoelectronic species have got, these are the species which have got same electrons, which have got the same number of electrons. And remember, isoelectronic species, for isoelectronic species, bond order is always the same. Bond order is always the same. Okay. For example, if I ask you to compare the bond order of CO and NO positive, CO and NO positive. CO is 8 plus 60, 8 plus 6 is 14 electron species. This is 8 plus 7, 15, 15 minus 1, 14. This also 14 electron species. And you know, all the 14 electron species, they have got bond order of 3. So their bond order is equal to 3. Perfect. So all the isoelectronic species will have the bond order of 3. I hope this is clear to everyone. Okay. Similarly, guys, for example, I'm writing O2. I'm writing O2 di-negative. I'm writing O2 negative, right? Can you arrange them? Can you arrange them on the basis of their bond order? See, this is a 16 electron species. This is 18 electron species. This is 17 electron species. 16 electron species have got the bond order of how much? 2. A 17 electron species have got the bond order of 1.5. 18 electron species have got the bond order of 1. So this is the bond order. 2, 1, 1.5. So if I talk about the order, if this is A, this is B, this is C. So bond order is going to be A has got maximum bond order followed by C followed by B. So what would be the bond length order? What would be the bond length order? I've told you already, bond order is inversely proportional to bond length. So reverse of it. So this A, this is C, this is B, right? What is going to be the bond dissociation energy order? I've told you already, bond order is directly proportional to your bond strength or bond dissociation energy, right? So bond dissociation energy will follow the same order, ACB. Perfect. So anything out of these can be asked in your exam. Okay. Anything out of this can be asked in your exam. I hope I'm clear with this. So guys, these were the short topics, short questions which can be asked from the chapter chemical bonding. I believe all of this is clear to everyone. Okay. Perfect. Now we are going to do one more chapter of your class 11th inorganic, and it's going to be your periodic table. But before starting this particular chapter, let's take a break for half an hour, right? And after that, let's fresh up and start this particular chapter. Okay? So periodic table. What's the time now? 8:10. I would want every one of you to be back exactly at 3:40. Okay, exactly at 3:40. All right. Fahim, hydrogen bond will be done in GOC, bro. That will be done in class 11th organic. Okay, I would want every one of you to be back on time exactly at 3:40 p.m. You guys can have your lunch, even I'll have my lunch too. Okay? I'll see you in some time. Is everyone back? Is everyone back? Yes? Just give me a second, guys. Just give me a second. All right, so let's start with the periodic classification now. Okay, and this is a very small chapter. It will not take more than 2.5 hours. Okay, because whatever I'm going to teach you, that's completely going to be exam oriented, no unnecessary stuff which is not asked in your exam. Okay. So tell me once in the chats, have you studied this particular chapter before or not? Have you studied this particular chapter before or not? Yes or no in the chats, quick. All right. Okay. Perfect then. Perfect, guys. So let's start with the chapter then, that is your periodic classification. My dear students, some basic information which I would want to give you first of all, related to the current periodic table which we have. The current periodic table which all of you would have seen many a times, right? Some basic information about that. Well, the first point which I would want you guys to remember, and please take a note of all these things. So people, this present form of period table, the modern period table, it is based on what? It is based on Bohr-Bury's electronic configuration. It is based on the Bohr-Bury's electronic configuration concept, and it's based on the atomic number. The current form of period table which we have, that is completely based on the atomic number as well as the Bohr-Bury's configuration concept. Well, you must be knowing, in the current period table which we have, there are in total 7 periods. There are, I would say, 7 horizontal rows. There are 7 horizontal rows, right? And there are 18 vertical columns. There are 18 vertical columns. Horizontal rows are what you call as periods. Horizontal rows are what you call as periods, and vertical columns are what you call as groups. So I would say in your modern period table, there are 7 horizontal rows, or I will directly say 7 periods, and 18 groups or 18 vertical columns. Okay? Yes, number 1. Number 2, in our current period table, there are 4 blocks. We divide our modern period table into 4 blocks, right? S block, P block, D block, and F block. What are our S block elements? I would say S block elements are the ones in which the last electron enters. The last electron enters into S subshell, or I'll say into S orbital. Your P block elements are the ones in which the last electron enters into the P orbital. Similarly, D block elements are the ones in which the last electron, incoming electron, enters into the D orbital. And your F block elements are the ones in which the last electron that enters into the F subshell, F orbital. So I would say our modern periodic table, it is divided into 4 blocks: S block, P block, D block, and F block. In case of your S block elements, last electron, the incoming electron, they enter into S subshell. Here they enter into P subshell. Here they enter into D subshell. Here they enter into F subshell. Let's have a look on the S block elements first. Let's have a look on the S block elements. Or before having a look on the S block elements, this is how your modern periodic table looks like. This is how your modern periodic table looks like. My dear students, as you can see, this group 1 and group 2, these two particular groups, 1 and 2, okay, they are basically your S block elements. They are basically your S block elements, right? Group 1 and group 2, it comprises of your S block elements. Perfect. Well, group 13 to 18, we call them as the P block elements, right? Group 13 to 18 are your P block elements. Similarly, group 3 till your group 12, they are your P block elements. And these elements which are separately mentioned over here, what do you call them as? You call them as the F block elements. You call them as the F block elements, right? This is the general look of your periodic table. Well, my dear students, in your F block elements, we have got 2 series basically. There are 2 series, lanthanoids and actinoids, right? Lanthanoids and actinoids. Well, my dear students, the elements which are between lanthanum and hafnium, the elements which are between the atomic number 57 to 72, the elements which are in between, excluding this one and this one, the elements which are in between atomic number 57 to 72, right? They are what we call as the lanthanoids. Similarly, the elements which are between these two, they are what we call as the actinoids. As you can see, your lanthanoid series and actinoid series. This is the broad look of your periodic table. Now we have to discuss about this periodic table in detail. We are going to discuss about this periodic table in very much detailed manner. So we'll start with our first block of elements, which are what you call as S block elements. First of all, S block elements are the ones in which the last electron enters into what? Last electron enters into S orbital. Last electron enters into S orbital. In our S block, we have got 2 groups. This is your group first, this is your group second. This is your group first, and this is what you call as your group second. My dear students, your group first elements, right? They are called as your alkali metals, and your group second elements, they are called as your alkaline earth metals. Now comes the first thing. My dear students, here, atomic number of hydrogen. That's 1. Now there are some magic numbers which you call as, I'm going to write. Let me write 2 here. Let me write 8. Again 8. 18. And that's what we need. Now have a look. 1 plus 2 makes it 3. 3 plus 8 makes it 11. 11 plus 8 makes it 19. 19 plus 18 makes it 37. 37, 10, 47 and 8 is your 55, right? Perfect. These are the respective atomic numbers of these elements. Now, if this is atomic number 3, this will be atomic number 4. If this is atomic number 11, this will be 12. This will be 19, 20, 37, 38, 55, 56. Okay. So this is how you get the atomic numbers of these elements. Okay. At the same time, for example, if I start with lithium, what is the electronic configuration of lithium? Hydrogen, helium, lithium, 1s2, 2s1. Outermost configuration is 2s1. If you talk about the outermost configuration of sodium, it is just going to be 3s1. If you talk about the outermost configuration of potassium, it's going to be 4s1. If you talk about rubidium, it's going to be 5s1. So in general, I must say the general outermost configuration of alkali metals. The general outermost configuration of alkali metals is going to be what? It's going to be NS1. NS1. Okay. Similarly, what is the outermost configuration of beryllium? It is 2s2. Outermost configuration of magnesium, 3s2. This is 4s2. This is 5s2. 6s2, right? So if I talk about the outermost configuration of group 2, your alkaline earth metals, it is NS2. It is NS2. So in general, the outermost configuration of your S block elements, in general, the outermost electronic configuration of S block elements, that is NS1 to 2. NS1 is for alkali metals, NS2 is for alkaline earth metals. Okay? I hope this is clear. Number 1. Number 2, look at your P block elements. Look at your P block elements from group 13 till group 18. From your group 13 till your group 18, right? This is 13th group, this is 14, this is 15, this is 16th group, this is 17th group, and this is 18th group. So I would say from your group 13 till group 18, what do we have? We have got P block elements. We have got P block elements. Now, first of all, let's have a look at their electronic configurations. See guys, if you talk about boron, what is the outermost configuration of boron? Hydrogen, helium, lithium, beryllium, boron. 5 electrons. So 1s2, 2s2, 2p1. So its outermost configuration is going to be 2s2, 2p1, right? What is the configuration of carbon? It is 2s2, 2p2. This is 2s2, 2p3. 2s2, 2p4. This is 2s2, 2p5. This is 2s2, 2p6. Okay. Now, just below boron, we have got aluminium. Right? Just below boron, we have got aluminium. If the configuration of boron was 2s2, 2p1, let me write it over here. For example, if I talk about boron, if boron's configuration was 2s2, 2p1, the element just below boron, that's aluminium. So aluminium's outermost configuration is going to be 3s2, 3p1. Similarly, gallium's outermost configuration is going to be, if this is 3s2, it's going to be 4s2, 4p1. Similarly, for example, if I talk about oxygen, what is the outermost configuration of oxygen? It is 2s2, 2p4. 2s2, 2p4. What is the element just below oxygen? That's sulfur. So sulfur will have 3s2, 3p4. What is the element just below sulfur? It is Se. It's going to be 4s2, 4p4. So in this way, you can write the electronic outermost configuration of all these elements. Okay. Now, my dear students, what is important here? These elements which I have mentioned over here, right? I'm sure you can see all these elements which I have kept in these boxes, right? The elements which I have kept in boxes, they are metalloids. The elements which are kept in boxes, what are they? They are metalloids. They are metalloids. They are metalloids. Okay. The elements which are above these metalloids, they are non-metals. They are non-metals. And the elements which are below these metalloids, they are metals. So I would say this is the only block. This is the only block which contains metals, non-metals, as well as metalloids. This is the only block which contains metals, non-metals as well as the metalloids. So my dear students, what is going to be the general outermost configuration of p block elements? As you can see, this is, for example, ns2 np1, ns2 np2, ns2 np3, ns2 np4, ns2 np5, ns2 np6. So in general, I would say the outermost configuration of p block elements is going to be ns2 np from 1 to 6. I believe this is clear to everyone. I believe this is clear to everyone. Right? I believe this is clear to everyone. Now, my dear students, if you talk about your D block elements, your D block elements, okay, your D block elements. In case of your D block elements, first of all, these elements which I've mentioned over here, they are your D block elements. The first series here, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. This is what you call as the 3D series. Right after this, you call this as the 4D series, and then you call it as the 5D series. So first of all, let's have a look on their electronic configurations and what all things you have to remember. If you look at the outermost configuration of scandium, what is the outermost configuration of scandium? 3D1, 4s2. Titanium, 3D2, 4s2. 3D3, 4s2. 3D5, 4s1. 3D5, 4s2. 3D6, 4s2. 3D7, 4s2. 3D8, 4s2. 3D10, 4s1. 3D10, 4s2. This is the outermost electronic configuration of your 3D elements. This is the outermost configuration of your 3D element, right? Now you can write the outermost configuration of all the elements just below them. For example, let's say I want to write the outermost configuration of, let's say, this molybdenum. What would be the outermost configuration of molybdenum? If this is 3D5, 4s1, this would be 4D5, 5s1, right? For example, let's say the outermost configuration of copper, that is 3D10, 4s1. If you want to write it for silver, it would be 4D10, 5s1, right? Similarly, Au, gold, it will be 5D10, 6s1, right? Okay. My dear students, this particular box which I've kept over here, you have to understand this as well, okay? What exactly is important here? I'll tell you what type of questions will be asked. First of all, I'm giving you the broader perspective of the periodic table. Remember all these points first of all. Okay. See, if I talk about the electronic configuration of nickel, we know that is 3D8, 4s2. Therefore, electronic configuration of palladium has to be 4D8. It has to be 4D8, 5s2. But this is not the electronic configuration of palladium. This is the actual electronic configuration of palladium. 4D10, 5s0. Okay. These are the exceptional electronic configurations you have to remember. I was expecting the platinum to have the electronic configuration of 5D8, 6s2. But this is not the electronic configuration of platinum. The electronic configuration of platinum is 5D9, 6s1. So these are the two exceptions which you have to remember in case of your D block elements, nothing else. Rest everything is same. Rest everything is same. Okay? Rest everything is same. For example, scandium, 3D1, 4s2. This Y will have 4D1, 5s2. Right? Titanium, 3D2, 4s2. This will be 4D2, 5s2. Perfect. Rest everywhere it's same. You just have to remember these two cases. Right? Palladium and platinum. Okay? My dear students, one more important thing. These D block elements, they are called as transition elements. These D block elements, they are called as the transition elements, except zinc, cadmium, and mercury. Zinc, cadmium, and mercury, these are not your transition elements. They are not the transition elements. Okay? D block elements are also called as transition elements, except your zinc, cadmium, and mercury. First of all, what are transition elements? I would say transition elements are the ones which have got incompletely filled d orbitals, in ground state or in common oxidation state. For example, talk about zinc. Where do I write it? Talk about zinc. For example, I'm writing zinc here. What is the configuration of zinc in ground state? Configuration of zinc in ground state is 3d10, 4s2, right? What is the most common oxidation state of zinc? The most common oxidation state of zinc is zinc dipositive. Zinc dipositive will be 3d10. Either in ground state or this most common oxidation state. Ground state or the common oxidation state. Do you see incompletely filled d orbitals or completely filled? You can see completely filled d orbitals. What are transition elements? Transition elements are the ones which have got incompletely filled d orbitals, either in ground state or most common. Here you do not have incompletely filled d. Here you do not have incompletely filled d. Right? So your zinc is not the transition element. Okay? So my dear students, remember, I can say all the transition elements are d block elements. All the transition elements are d block elements. But all the d block elements are not the transition elements. Remember this particular point. Okay? Remember this particular point. I believe it's clear to everyone. All the transition elements are d block elements, but all the d block elements are not the transition elements. Am I clear with this? Am I clear with this? Quickly in the chats. Quickly in the chats. Everyone. Okay, perfect. And guys, this is the general outermost configuration of the d block elements, n-1 d 1 to 10, n is 0 to 2. This is the general outermost configuration of your d block elements. Now similarly, when it comes to your ebb block elements, these are your ebb block elements. Leave the lanthanum and actinium aside. Okay. After these, your ebb block elements will start. Your ebb block elements, your lanthanoid series actually starts from atomic number 58 till your atomic number 71. So this first series is your from atomic number 58 till your atomic number 71. These are all your lanthanoids. Similarly, from atomic number 90 till your atomic number 103, we have got actinoids. Okay, we have got actinoids. Remember, this lanthanum and actinium, they are not your ebb block elements, right? I should keep star over here. Star means after lanthanum, your ebb block series starts. After lanthanum, your ebb block elements start. Lanthanum has got the atomic number of 57. So after atomic number 57, your F block elements will start. Right? So this lanthanum in the actual period table is here at this particular position. This is your lanthanum, and I'm keeping star over here. Atomic number 57. After 57, there'll be 58. But that 58th element is here. Right? So after 57, ebb block elements are going to start. Perfect. After 57, ebb block elements are going to start. So if I ask you, in which group these ebb block elements are there? In which group they belong to? Ebb block elements, they belong to which group? They basically, after lanthanum, they are starting. So lanthanum is coming in third group. Right? Right, people? If I ask you in which group they belong to, what will be your answer? All the ebb block elements, they belong to third group basically. They belong to third group, or you can say third B, 3B. Right? And the general outermost configuration of the ebb block elements, This is something which you need to remember as well. N minus 2 F1 to 14, N minus 1 D 0 to 1, N is 2. I'm not going into the details of the electronic configuration of these elements, right? That you will study in your F block. Now comes something important from which questions come. Till now, whatever I was telling you, that's all like complete basics, some basic things which you need to know. Now comes the actual stuff. The first question which is asked, what is that? How do we calculate, how do we predict the period number and the group number of an element? How do we predict the period number or the group number of the element if its electronic configuration is given? If you are given with the electronic configuration of an element, from the given electronic configuration, you need to predict the group number and period number of the element. How exactly you guys are going to do that? See guys, this is important. Whenever you are supposed to check the period number of an element, to which period an element belongs to. Does it belong to first period, second period, third period, or whatever period? Period number is always equal to the highest value of principal quantum number. For example, let's say this is outermost electronic configuration of some element. What is its highest principal quantum number? 3. I would say the element whose electronic configuration is given to me, its period number is 3. Similarly, look at this particular configuration which is given to me. This is the electronic configuration of some element which is given to me. Now look at this, right? What is the highest value of principal quantum number here? That's 4. So I would say period number of this particular element would be 4. So this element would be belonging to period number 4. Similarly here, highest value of principal quantum number is 5. So period number of this particular element is nothing but 5. So first thing, whenever electronic configuration of an element will be given to us, right? And from the electronic configuration, you are supposed to check the period number. What are we supposed to do? Highest value of principal quantum number gives me the period number of an element. That's it. Highest value of principal quantum number gives me the period number of the element. Point number 1. Now the point is, how do we get the group number of an element? How do we get the group number of an element if its electronic configuration is given? For that, you have to remember certain cases. Some things you have to remember. Period number is highest value of principal quantum number. Okay. Now, how do we get the group number? My dear students, in case of your S block elements, group number is equal to number of electrons in ns orbital. Number of electrons in ns orbital. Number of electrons in ns orbital. For example, this is, I've got an element whose electronic configuration is this. This is the electronic configuration. See guys, first of all, if you see, the last electron has entered into the S subshell. If last electron has entered into the S subshell, so I would be calling this particular element as the S block element. So it is first of all the S block element, number 1. It's S block. The highest value of principal quantum number is 4. So the element belongs to period number 4. Element belongs to period number 4. What about its group number? Group number is going to be the number of electrons in ns. This is your ns. In ns, there is 1 electron. So group number of the element whose electronic configuration is given is 1. So the element belongs to first group. So it's an alkali metal. Element is an alkali metal. Okay. Similarly, for example, this is the electronic configuration that's given to me. The last electron has entered into the S subshell. So it is again the S block element. It is again the S block element, right? The highest principal quantum number is 5. So period number is 5. What about the group number then? Group number is equal to the number of electrons in ns. So in ns, you have got 2 electrons. So group number is 2. Group number is 2. So this particular element whose electronic configuration is given to us, it belongs to second group. Okay. Talk about the p block elements. In case of p block elements, your group number is equal to 10 plus sum of ns and np electrons. 10 plus sum of ns and np electrons. For example, let's say we have got the element whose electronic configuration is given to us. Outermost, 4s2, 4p2. 4s2, 4p2. What is the highest value? First of all, last electron has entered into the p subshell. If the last electron has entered into the p subshell, it is going to be the p block element. Right? Number 1. What is going to be the period number? Period number is the highest value of principal quantum number 4. What is going to be the group number? Group number will be equal to 10 plus ns plus np electrons. This is ns, this is np. ns carries 2, np carries 2. So 10 plus 4 makes it 14. So the element belongs to 14th group. The element belongs to 14th group. Okay. Similarly, 3s2, 3b5. Last electron has entered in the p subshell. So it's again a p block element. So what is its period number first of all? Period number is equal to highest value of principal quantum number, that is 3. What about its group number? Group number is going to be equal to 10 plus ns plus np. So 5 plus 2 is 7. So 10 plus 7 makes it 17. So this element belongs to 17th group. Right? This element belongs to 17th group. Similarly, my dear students, if I talk about the d block elements, in case of your d block elements, your group number is nothing but it is sum of n minus 1d and ns electrons. Sum of n minus. In S block, it was ns electrons. Here it is 10 plus ns plus np. In D block, it is n minus 1d and n minus 1d plus ns electrons. Have a look. Let's say we have got an element whose configuration is given to us 4s2, 3d6. 3d6. That means the last electron has entered into the D subshell. Right? 3d6 is iron. 3d6, 4s2. That's iron basically. Right? So, first thing, it's a D block element. Number 1. Highest value of principal quantum number is 4. So, period number is 4. What about the group number? What about the group number? See, if this is n, this is going to be n minus 1. If this is n, this is going to be n minus 1. So, n minus 1 d electrons, that is 6, plus ns electrons, that is 2. 6 plus 2 is 8. So, this element belongs to 8th group. This element belongs to 8th group. And as I told you already, all your F block elements, they belong to group 3. And your F block elements are basically from the atomic number 58 to 71 and 90 to 103. Right? Lanthanoids and actinoids. Is this particular stuff clear? Tell me once in the chats, everyone. Tell me once in the chats quickly. Is it clear? So this was how to check the period number and group number of an element if its electronic configuration is given. Okay? If its electronic configuration is given. Now comes one more point. If, for example, electronic configuration of an element is not given, imagine atomic number of an element is given. Imagine atomic number of an element is given. And what do we do at that time? Imagine electronic configuration of element is not given. Atomic number of an element is given. From the atomic number, how do we identify the period? How do we identify the group? Right? Let's have a look on that. See guys, first of all, you should remember these noble gases. Okay? These noble gases. Helium, atomic number 2. Again, you can do your normal stuff, right? You can do your normal stuff. This is 2, 8, 8, 18, 18, 32, 32, right? See, if helium has atomic number 2, 2 plus 8 makes it 10, 10 plus 8 makes it 18, 18 plus 18 makes it 36, 36 plus 18 makes it 54, 54 plus 32 makes it 86, right? So first of all, these are your noble gases. These are their respective atomic numbers, right? And these are their period numbers. Helium belongs to period number 1, neon period number 2, argon period number 3, krypton period number 4. This is first thing which you need to remember. This is the first thing which you need to remember. Now after this, understand what exactly I'll be saying. Something important I'm going to tell you guys. Something important I'm going to tell you. First of all, if the atomic number of an element, lies between, if the atomic number of an element is between 58 to 71, then these are the F block elements. Which elements? Your lanthanoids, and lanthanoids, they belong to 6th period. Your lanthanoids, they belong to 6th period. if the atomic number is between 90 to 103, 90 to 103, that means they are your actinoids. And actinoids they belong to your seventh period. They belong to your seventh period. Right? For example, 93 atomic number. What is the period number? Period number 7. 97, period number 7. 65 atomic number, period number 6. 70, period number 6. Okay? Now, my dear students, if atomic number of an element does not belong to this category, nor belongs to this category, if atomic number of an element is neither coming in between this, nor coming here in this category, then how do we get the period number? Then period number of an element is nothing but, period number of an element is going to be the period number of next inert gas. It is going to be the period number of next inert gas. What does that mean? For example, you have got an element whose atomic number is 44. You have got an element whose atomic number is 44. 44 is neither coming in this category, nor is coming in this category. 44 is neither coming in this category, nor is coming into this category. Then, period number of an element whose atomic number is 44 will be equal to period number of next inert gas, right? Next inert gas. After atomic number 44, which is my inert gas? After atomic number 44, my next inert gas is xenon. Xenon belongs to fifth period. So I would say this element also will belong to period number 5. Do you understand this? Do you understand this? Let's say I've got the element whose atomic number is 32. 32. 32 is neither coming in this category, nor is coming in this category, right? So period number of this particular element whose atomic number is 32 will be equal to the period number of next inert gas. What is the next inert gas after 32? That is 36. 36 means krypton. Krypton belongs to period number 4. So I would say period number of this particular element would be 4. Am I clear with this? Am I clear with this? So this is how you check the period number of an element if its atomic number is given. Now, how do we check the group number of an element if atomic number is given? How do you check group number of an element if its atomic number is given? See guys, first thing, 58 to 71 or 90 to 103. They are your F block elements, and F block elements, they belong to third group. Third group, or you can say 3B. Right? Perfect. This is something which we already know. Now, if atomic number is between 104 to 118, if atomic number of an element is between 104 to 118, then group number is nothing but the last 2 digits. Group number is nothing but the last 2 digits. For example, I've got the element whose atomic number is 107. Whose atomic number is 107. 107 is coming in between this, right? What are the last 2 digits? 7. So I would say group number of this particular element will be 7. Element belongs to 7th group. Let's say I've got 111. 111. Check the last 2 digits. 11. So this particular element belongs to 11th group. Perfect. Let's say I've got 116. Check the last 2 digits. So this particular element belongs to group 16. Perfect. Right? So you should know this particular stuff as well. I hope this is clear. Now after this, my dear students, if atomic number of an element neither comes in this category, nor comes in this category, nor comes in this category, then how do we get the group number? Then how do we get the group number? Group number then is going to be 18 minus next inert gas minus atomic number. Now you must be thinking, what is that? You must be thinking, what is that? For example, Z is equal to 44. Atomic number of an element is equal to 44. Let's say atomic number of an element is 44. 44 neither comes in this category, nor comes in this category, nor comes in this category. Now, how do I get its group number? First of all, let me check the next inert gas after 44. What is my next inert gas after 44? That is 54. So next inert gas is 54. Nig is 54. Right? If you got Nig, so group number is equal to 18 minus 54 minus atomic number, that is 44. So 54 minus 44 is 10. 18 minus 10 is 18 minus 10 is 8. So I would say this particular element belongs to which group? It belongs to 8th group. 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 Right? For example, you have got the element whose atomic number is 32. Atomic number is 32. What is the next inert gas after 32? You check it. After 32, the next inert gas is 36. So NiG is 36 here. NiG is 36. So I would say group number is nothing but it will be 18 minus 54 minus what did I, oh, sorry. It's going to be 18 minus NiG is 36 minus Z is 32. Minus Z is 32. So how much it comes out to be? This is 836 minus 32 is 4. 18 minus 4 is 14. So this particular element belongs to group 14. So like this, you can identify your groups if atomic number is given to us. Okay? Now, my dear students, the naming of this is the easiest one. You know it already. You know it already. This is the easiest one. Naming of elements with atomic number greater than 100. So first of all, you have got the element whose atomic number is 101. How do I name it? How do I name it? There are some prefixes which you are going to use. Like for 0, we use the prefix as nil. For 1, you use the prefix as un. For 2, you use the prefix as bi. For 3, you use the prefix as tri. For 4, you use the prefix as quad, pent, hex, sept, oct, n. And at the end, suffix is to be used as IUM. For example, this is the easiest among all, right? Let's say you have got atomic number 101. What would be its name then? What would be its name? See, for 1, I'll be writing un. For 0, I'll be writing nil. For 1, I'll be writing un. At the end, I'll be writing IUM as a suffix. So, un, nil, unium. Un, nil, unium. This is going to be its symbol. This is going to be its symbol, right? For example, we have got 107. 107. 1 means un. 0 means nil. 7 means sept. At the end, IUM. What would be its symbol? Un, nil, septium. Un, nil, septium. Okay. For example, you have got an element with atomic number 115. 115. So 1 means un. Another one means un. 5 means pent. Right? 5 means pent. At the end, IUM. So un, pentium. So UP is going to be its symbol. Is it clear? This is the easiest among all the topics. This is easiest among all the topics. You know it already. Is it all clear, guys? Is it all clear? Questions are asked from all this. Whatever things I taught you till now, how to identify the block, period, group, if atomic number is given, if electronic configuration is given, all these things are asked in your exam, guys. And this is the most volatile part of the chapter, which you forget easily. Okay? So you have to revise it 3-4 times, then only you can remember all these basic formulas which I gave you, right? And I hope by looking at the formulas, this topic becomes clear. Otherwise, when I was in preparing for my JEE examination, it was really headache for me to get the group number, period number, etc., right? That was okay. Now comes to one more topic, that's your screening effect or shielding effect, right? This one easiest topic, and I'm sure you all would have studied it before also, right? So let me give you an idea of what the shielding effect is all about and where do we use it. Yeah, let's get to know about this. See guys, what happens in shielding effect. See what happens here. Understand what I'll be saying, okay? Understand what I'll be saying. First of all, if you look at all these things, right? Let's not look at all these things. You just focus on what I say. For example, this is the nucleus. This is the nucleus, right? Inside the nucleus, what do we have? Inside the nucleus, we have got protons. Inside the nucleus, we have got protons. Okay? For example, this is the outermost shell containing one electron. Outermost shell containing one electron. Okay? I'm assuming that in between nucleus and this electron, in between these two, there are no other electrons. I'm assuming in between nucleus and this outermost electron, there are no electrons, for example. So can I say this nucleus will be wholly and solely attracting this electron towards itself? Absolutely. This nucleus will be right now devoting all its energy to attract this electron towards itself. Yeah? Right? For example, just to make you understand, let's say this nucleus is attracting this electron towards itself by the force of 5 Newton right now. Just to make you understand. Right now, the nucleus is attracting the electron with a force of 5 Newton, let's say, just to make you understand. Now, people, for example, imagine a scenario like this. Let's say there is an inner shell, and the inner shell also contains some electrons. Let's say there are some inner shell electrons also present. Now, if there are some inner shell electrons also present, how many forces this particular electron will be experiencing now? One force will be the force of attraction from the nucleus. Between this electron and this electron, there will be repulsion, there will be repulsion, there will be repulsion, there will be repulsion, there will be repulsion. Now tell me, in presence of these inner electrons, will this outer electron experience same 5 Newton or less than that? What do you think? In presence of inner electrons, when inner electrons are there, now repulsions arise in here. Repulsions arose, right? Now force of attraction on this outermost electron, will it be same 5 Newton or less? It will be less. Let's say it will be now 2 Newton. This was in absence of inner electrons. In absence of inner electrons. This is in presence of inner electrons. In presence of inner electrons. So due to the presence of electrons, inner electrons, the force experienced by the outermost electron decreases. And this effect is what you call as the screening effect. Okay? Perfect? Right? So the tendency of inner electrons to protect the outer electron, from the charge of the nucleus is what you call as shielding. Now, my dear students, there are two types of shieldings. One is called as effective shielding. One is called as pore shielding. If this shielding is poor, what do you think? So technically, if I say these inner electrons, they are creating a type of shield over here. Right? Okay? If shielding is poor, force of attraction on the outer electron would be more. Force of attraction on the outer electron more means effective nuclear charge would be more. I hope you are getting all this. Similarly, what did I say? I think I told the reverse thing. Did I say the reverse stuff? If shielding is poor, okay? If shielding is poor, force experienced by the outermost electron would be more. Force experienced by the outermost electron means effective nuclear charge is more, right? So I think I have reversed this stuff. Z effective here Z effective here. Due to poor shielding, Z effective more. Here, Z effective will be less. Okay? Perfect. Now, my dear students, understand few more things. Understand few more things. First of all, for the same shell, what about the shielding effect of these orbitals? What about the shielding effect of the orbitals? We say S orbitals, they show maximum shielding. Why? They show maximum shielding. Why? Because they are closest to the nucleus. Because they are closest to the nucleus. They are closest to the nucleus, right? Your D and F, we say they show ineffective shielding. They show they are ineffective shielders, whereas your S and P, they are effective shielders. Okay? S and P, they show good shielding, right? Effective shielding. These two show ineffective or poor shielding. It's pretty much simple. If S electrons are closer to the nucleus, they are going to shield the maximum. They are going to shield the maximum, right? They are going to shield the maximum. Your D and F, they are far from the nucleus, so they are going to be the poor shielders. Now, guys, one thing which you should remember, this effective nuclear charge. Effective nuclear charge. See, first of all, you can relate effective nuclear charge like this. If I ask you, there are some inner shells containing electrons, okay, and there is the outermost shell containing an electron. If I say the shielding is less, shielding of inner electrons is less, shielding done by inner electrons is less, what does that mean? That means force of attraction on the outermost electron is more, right? Force of attraction on the outermost electron is more. Perfect. If the shielding done by inner electrons is more, if the inner electrons are doing effective shielding, force experienced by the outermost electron will be less, right? At that time, force experienced by the outermost electron would be less. Perfect. Now, guys, I just want to tell you one point over here. What is that? Have a look. Let's say you have got an atom X, which has got 10 protons and 10 neutrons. Sorry, which has got 10 protons and 10 electrons. You have got an atom X, which has got 10 protons, 10 electrons, right? Now, for example, you are taking an electron out, it becomes X positive. Now, protons are still 10, but electrons are now 9 only. I would say, initially 10 protons were holding 10 electrons. 10 protons were holding 10 electrons. Now, the same 10 protons are holding 9 electrons only. Initially, 10 were holding 10. Now, the same 10 protons are just holding 9 electrons. Let's say force experienced by the electrons here would be more. What does that mean? That means effective nuclear charge is more. So basically, what is happening? When a parent atom is converted into its cation, effective nuclear charge increases. Similarly, I must say, when the parent atom is converted into its anion, effective nuclear charge decreases. When the parent atom is converted into its cation, effective nuclear charge increases. When the parent atom is converted into its anion, effective nuclear charge decreases, right? So just tell me one thing. If I talk about effective nuclear charge, can I say it is directly proportional to positive charge? Inversely proportional to negative? Effective nuclear charge, it's directly proportional to positive charge. See, when positive is getting generated there, effective nuclear charge is increasing. So more positive, more effective nuclear charge, right? More negative, less effective nuclear charge. Okay, just remember this particular point. And if you remember this particular point, you should be easily solving this question. N positive, N negative. N positive, N and N negative. What is the order of their Z effective? More the positive charge, more the Z effective. So positive, neutral, then negative. This is the order of Z effective. Right? As simple as that. Similarly, this is your asked question. This is your asked question. H negative, Li positive, B di positive, B tri positive. If you look carefully, H negative carries 2 electrons. Li positive also carries 2 electrons. This also carries 2 electrons. This also carries 2 electrons. And if electrons are same, I would say these species are your isoelectronic species. These species are your isoelectronic species, right? These species are your isoelectronic species. And if you want to check the Z effective of the isoelectronic species, more the positive charge, more the positive charge, more is the Z effective. So positive charge is maximum here, Z effective is maximum here. Similarly, positive charge is maximum here, Z effective is maximum here. More the positive charge, more the Z effective. Simple. Right? Perfect. I hope this is clear. What do you think is the answer of this particular question? Think over it. Think over it. What do you think would be its answer? What do you think would be its answer? In sodium atom, 1s2, 2s2, 3p6, 1s2, 2s2, 2p6, 3s1. In sodium atom, the screening of 3s is due to all the inner electrons. All the inner electrons. Achha, by the way, one more thing. There will be a lot of students among you who would have studied the Slater's rules, etc., to get the sigma and all. That is irrelevant. That's not in your syllabus. So do not waste your time in remembering the Slater's rule and something like that. Right? That's a wastage of your time. Nothing else. So highly recommended to leave that when it comes to your NEET examination. Okay? So answer of this particular question you got. That's great. All right. Now comes your term atomic radius. What is the atomic radius? How do you define the atomic radius? How do you exactly define? See, in simple words, I can define it as the radius of atom. The radius of atom. In simple words. Or the radius of atom, or I can define it like this. The distance from the nucleus. The distance from the nucleus to the outermost shell. The distance from the nucleus to the outermost shell. But the point is, in an isolated atom. Isolated atom means that atom which is not in bonded state. The distance between the nucleus and the outermost shell, right, in case of isolated atom. Now, if I ask you one thing, since I'm telling you, this is the nucleus. For example, this is the outermost shell. First of all, we cannot define the outermost shell basically, right? The boundary of the atom is not defined as far as your atomic structure is concerned, right? But still, for example, for your convenience, let's say this is the outermost shell, for example. This distance from here to here. This distance from here to here. From the center of nucleus till here is what you call as atomic radius. But this atom has to be in which form? Isolated form. You tell me one thing. Can you get the atom in isolated form? Can you get the atom in isolated form? Can you get the atom in isolated form? You cannot get the atom in isolated form. If you cannot get the atom in isolated form, that means you cannot calculate this atomic radius experimentally. You cannot calculate the atomic radius experimentally because it is very, very, very difficult to get the atom in isolated form. One more thing. You cannot define this particular surface. You cannot define this particular surface of the atom. You cannot define the outer surface of the atom. Right? You cannot do that. Because we talk in terms of probabilities. We talk in terms of electron clouds. We say electron can be sometimes here, sometimes here, sometimes here, sometimes here, sometimes here. You cannot define it exactly. You cannot say this is the outermost surface of the atom. No, you cannot do that. Okay? So remember, atomic radius, it cannot be measured experimentally. Since it is very difficult to get the atoms in isolated form because atoms are in bonded conditions. If atoms are in bonded conditions, you know, some of the atoms they form covalent bonds, some of the atoms they form metallic bonds, right? Since atoms are always in bonded conditions, if the atoms are in bonded conditions, therefore we are going to define atomic radius also in the bonding conditions. Atoms exist in bonded state. Therefore, atomic radius is also defined under bonded conditions only. Atomic radius is also defined under bonded conditions. Number one, covalent radius, metallic radius, van der Waals radius. Covalent radius is defined for those atoms which form covalent bonds. Covalent radius is defined for those atoms which form covalent bonds. And which atoms form covalent bonds? Your non-metals. Generally, your non-metals, they form covalent bonds. So, covalent radius is defined for generally for the non-metal atoms, right, which form the covalent bonds. Metallic radius will be defined for the metals, and your van der Waals radius, it will be defined for your noble gases as well as non-metal. Now, one by one, we have to discuss all these three radius. First one is your covalent radius. What is covalent radius? What is covalent radius? First thing which I told you, covalent radius is defined for non-metal atoms. It is defined for those atoms which are held with the help of which bond? Which are held by means of covalent bond. Which are held by means of covalent bond. Right? Which are held by means of covalent bond. For example, have a look. I'm writing the heading as covalent radius. Covalent radius. First point, it is defined generally for non-metal atoms, right? Which are held with the help of covalent bonds. Okay? For example, I'm taking a homonuclear atom, homonuclear molecule. For example, I'm taking a homonuclear molecule. Let's say this is one of the atom A. This is one of the atom A. Let's say this is the atom A. Similarly, we have got atom B as well. And this atom B has formed. Just a second. This atom B has formed a covalent bond here. See, this was atom A, this also atom A, and they are held together with the help of covalent bond. That's why I have shown this overlapping here. Right? Let's say this is the nucleus of atom A. This is the nucleus of the atom A as well. Perfect. So right now they have got covalent bond in between. There's a covalent bond in between. So what I'll be doing? This is first of all the molecule. What is the name of this molecule? Let me call this as A2 molecule. Now, how do I define the covalent radius? What I'll be doing? I'll be getting the distance between these two nuclei. I'll be calling the distance between these two nuclei. I'll be calculating distance between these two nuclei, which is what I call as bond length. Right? The distance from here to here is what I call as bond length. And once I get the bond length, I'll be dividing this bond length by 2. That is something which I call as R covalent. R covalent is nothing but it is equal to your bond length divided by 2. Right? Or I'll say DAA divided by 2. This is how you get your covalent radius in case of your homonuclear molecules. Okay? Perfect. Right, people? Second comes your metallic radius. Metallic radius is defined for metals. What is it? It is half the internuclear distance between the two adjacent metallic atoms in the crystalline lattice. Let's say this is the crystalline lattice. And these are the constituent particles. These are the constituent particles of your crystalline lattice, right? Now, in the crystalline lattice, these metal atoms, they won't be merging into each other. They'll be just touching each other. There is no overlap. There is no overlap in case of the solids. Okay. Now, what do I need to do over here? I need to get this distance, this internuclear distance, right? I need to divide it with 2. When I divide this with 2, what I'll be getting? I'll be getting again the metallic radius. I'll be getting again the metallic radius. Now, in case of covalent radius, there was overlapping. In case of metallic radius, there is no overlapping. They are just touching each other. They're just touching each other. So, which radius would be more? I would say your metallic radius would be more than that of your covalent radius. Your metallic radius would be more than that of your covalent radius. This again one important point which I would want you all to remember. Okay. Similarly comes your van der Waals radius. My dear students, van der Waals radius is defined for noble gases present in which state? Noble gases present in solid state. What is meant by that noble gas present in solid state? For example, I've got a noble gas neon, right? It's a gas, we know, but we can solidify it. We can convert this into any solid, right? So this is noble gas in solid form. This is noble gas in solid state. Okay, remember this particular point. So it is defined for the noble gases. It is defined for noble gases or gaseous molecules present in solid state. Present in solid state. For example, this is your neon, one neon atom, this one more neon atom, and I believe over here there is a weak van der Waals force of attraction between them. What you need to do here again is you'll be calculating this distance and then divide it with 2, right? What do you get? You'll be getting the, what do you call this as? You'll be getting the van der Waals radius over here. You'll be getting the van der Waals radius over here. Or it's not necessary that you'll be having these noble gases only. For example, I've got Cl2 molecule. This, for example, Cl2 molecule, ClCl, right? This is Cl, this is Cl. Between them, there is a covalent bond. Between them, there is a covalent bond, right? Similarly, one more ClCl. Between this Cl and this Cl, there is a covalent bond. Now, in between these two Cl molecules, which force arise? It is going to be van der Waals force which arise here. It is going to be van der Waals force which arise here. Perfect. In between these two, there is van der Waals force. Yeah. Right? Some spammers have come. Welcome, spammers. Okay, so this is your Cl2 molecule, this is your Cl2 molecule. Between this Cl and this Cl, there is a covalent bond. Between this Cl, this Cl, there is a covalent bond. Between these two Cl2 molecules, there is van der Waals force. Perfect. Now, if there is van der Waals force, what do I need to get? I need to get the internuclear distance divided with 2, and I'll be getting the van der Waals radius, right? Like this over here. Like you have got these two iodine molecules. Between these two iodine molecules, what am I exactly going to do? What am I exactly going to do? I'll be getting this particular distance first and then divide it with 2. When I divide it with 2, I'll be getting the van der Waals radius. And generally, it's observed, see, from here to here, you are defining covalent radius. Here, you are defining covalent radius. Here, in between, you are defining van der Waals radius. And remember, van der Waals radius is almost equal 2 times the covalent radius. Van der Waals radius is almost equal 2 times the covalent radius. Remember this particular point as well. So, finally, I can say, in your covalent radius, merging is there, right? Okay. In your metallic radius, these metal atoms just touch. When you define the van der Waals radius, they do not touch. So I would say your covalent radius will be least, right, among all. Then your metallic radius, then your van der Waals radius. So van der Waals radius is maximum among all the radiuses which we have. Okay. Right. I hope I'm clear with this. Now guys, these sort of questions also come sometimes. Let's say we have got an atom A. do not look at the headings and all stuff. Have a look on what I say. You have got A. Here you have got A positive, A di positive, A tri positive. So charge on moving from left to right. What is happening to charge? Positive charge is increasing. If positive charge is increasing, effective nuclear charge is increasing. If effective nuclear charge is increasing, that means force of attraction by nucleus on the outer electron will be increasing. Means outer electron will be coming closer. Distance decreases. Distance decreases. Ionic radius decreases. So size decreases basically, right? So among all, which one of the following will have least size? A tri positive will have least size. A tri positive will have least size. Okay? Among all these ions. I hope this is clear to everyone. A positive, A di positive, A tri positive. Maximum positive charge, maximum effective nuclear charge. Maximum effective nuclear charge means more attraction between nucleus and outermost electron, right? So lesser will be the size. So its size will be the least. So in short, you can remember it like this. More the positive charge, lesser the size. More the positive charge, lesser the size. That's it. Okay? I hope this is clear. Now guys, I just want you guys to think over one thing. You have got sodium, you have got Na positive, you have got Na di positive. If I talk about size, Na di positive will have the least size. Is that? Na di positive will have the least size, right? As compared to Na positive, as compared to sodium. But the size difference between sodium and Na positive is too much. Size difference between sodium and Na positive is a lot. Why is that? Why is that? In case of sodium, do you see how many shells you have? 1, 2, and 3. In case of Na positive, you have taken this electron out. There are only 2 shells. So shell is decreasing basically. From Na to Na positive, shell is decreasing. That's why size decreases drastically from Na to Na positive. Okay? So remember, due to the change in shell number. Similarly, you have got Mg, Mg di positive, Mg positive, Mg di positive. What is the configuration of Mg? 3s2. Mg positive will be 3s1. Mg di positive will be, take this 3s1 out, 2p6. We already know Mg di positive will be having least size. Comparatively, Mg positive will have more size. Comparatively, Mg will have more size. But where would be the size difference more? Where would be the size difference more? In first and second? No. Because 3 shells here also, 3 shells here also. But here you have got 3 shells. Here you have got only 2 shells. So shell number changes in between these two. So there's a massive size difference between Mg positive and Mg di positive. Remember this particular stuff as well. This is important. Okay. Now similarly, till now I was talking about the cations. You can talk about the anions as well, right? I've told you already, your Z effective is inversely proportional to what? I've told you your Z effective is inversely proportional to negative charge, right? More the negative charge, lesser the Z effective, right? More the negative charge, lesser the Z effective, lesser the Z effective. That means lesser will be the attraction between nucleus and outermost electron. If lesser is the attraction, more will be the size. More would be the size, right? Perfect. So for example, you have got X negative, X di negative. Where is negative charge more? Here negative charge is more. More the negative charge, lesser the Z effective. So its effective nuclear charge is less. If its effective nuclear charge is less, its size would be more. Its size would be more. Perfect. So in short, more the negative charge, more is going to be the size. Right? More the negative charge, more is going to be the size. More the positive charge, lesser is going to be the size. More the positive charge, lesser is going to be the size. Okay? Let's say O negative, O di negative. More the negative charge, more the size. Right? N negative, N di negative, N tri negative. More the negative charge, more is going to be the size. Simple. Okay? And already I have discussed about the isoelectronic species as well. Right? More the positive charge. In case of isoelectronic, more the positive charge, More the effective nuclear charge. More the effective nuclear charge, lesser the size. More the positive charge, lesser the size. So these are all isoelectronic. They have same electrons. So directly see the positive charge now. Positive charge is maximum here. More the positive charge, more the effective nuclear charge, lesser the size. Right? More the negative charge, lesser the Z effective, more the size. So these are all isoelectronic species, and this is how you can give the order to their size as well. I hope I'm clear with this. And this is complete basic now, which you can easily do. Okay. All right. One thing more. If you talk about the general trends in period table about the atomic radius, see, one thing which all of you must be knowing, on moving from left to right in the period table, what happens to size? Size decreases generally. On moving from top to the bottom in the period table, size increases because the shell number increases. Right? Because the shell number increases. This is something which I believe all of you would be already knowing. On moving from left to the right, your size generally decreases. Top to bottom, since shell number increases, therefore, top to bottom, since shell number keeps on getting added, so your size also increases. So tell me the answer of this. Achha, answer is already written. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. They belong to same period. From left to right, size decreases. From left to right, size decreases. Right? So lithium will be a maximum size, then beryllium, boron, carbon, nitrogen, oxygen, fluorine. Right? After fluorine, what comes? Neon. After fluorine, what comes? Neon. Right? Think about it. Can I say neon will have least size among all? If neon is also there, if neon was also there, will neon have least size? Will neon have least size? No, neon will have the largest size among all. This is the exception which I'll deal in some time. Neon will have the largest size among all because neon is a noble gas. For noble gases, what do we define? We define van der Waals radius. Van der Waals radius is largest among all the radiuses. Okay? So I'll talk about that in some time. Tell me about this one. Lithium, sodium, potassium, rubidium, cesium, group first elements. Down the group, size increases. So this is the general order. Down the group, size increases because shell number increases. Okay, this is a general order. Now, some exceptions which I wanted to discuss with you. See, size of neon, as I told you, size of neon is far greater than that of fluorine. Okay, why is that? Because neon being a noble gas, for noble gas, what do we define? We define the van der Waals radius. And van der Waals radius is maximum among all the radiuses. Okay, so you need to remember this. Now, similarly, when it comes to your transition elements, what about their size irregularity? What happens basically? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Right? These are your 3D elements. Okay. See, from scandium till iron, I would say. From scandium till iron. Remember all this. From scandium till iron. Effective nuclear charge dominates over screening. Okay, and if effective nuclear charge dominates over screening, what does that mean? That means size initially decreases. Then in case of your iron, cobalt, nickel, I would say Z effective and screening, they counterbalance, due to which size almost remains the same. And from copper to zinc, I would say screening dominates over Z effective and hence size increases. This is your 3D. Remember this particular stuff, and you can remember it with the help of graph. From scandium till iron, it decreases. then iron, cobalt, nickel, same, then again it increased till zinc. Okay, remember this particular order. This is for your 3D series. This is for your 3D series. This is one important point which I'm going to tell you now. If you talk about your D block elements, in case of a D block elements, you've got three series, 3D series, 4D series, 5D series, right? See, leaving this particular group aside, when you move from 3D to 4D, 3D to 4D, 4D to 5D, what should happen to size? Size should increase. Moving from 3D to 4D, 4D to 5D. So here, on moving from 3D to 4D, 4D to 5D, size should increase. Size should increase. Size should increase. So if I compare the size of these three, what is the expected size? I'll say hafnium should have maximum size, followed by zirconium, followed by titanium. This is the expected order. This is the expected order. This is the expected order. But this is not the actual order. This is not the actual order. Why is that? Why is that? Do you remember the atomic number of lanthanum? It was 57. After lanthanum, there are 14. There are your F block elements. After lanthanum, what are there? There are F block elements. Right? After your lanthanum, there are F block elements. And after those F block elements, hafnium comes. After those F block elements, hafnium comes. So guys, if you think logically, from titanium to zirconium, shell number is increasing, size is increasing. Now from zirconium till hafnium, can I say from zirconium till hafnium, 14 F block elements are coming in between, 14 lanthanoids are coming in between. And in those lanthanoids, the outermost electron goes in F subshell. The outermost electron goes in F subshell. And your F subshell is pore shielder. F subshell is pore shielder. If shielding is poor, effective nuclear charge increases. Force of attraction between nucleus and outermost electron increases. So size should decrease. Size should decrease. Normal trend shows from zirconium to hafnium, size should increase because shell number is increasing. But due to the lanthanoid contraction, the size should decrease. Therefore, zirconium and hafnium, their size is almost the same. Their size is almost the same. Similarly, vanadium, niobium. Niobium will have more size than vanadium, but niobium and this Ta, they'll be having almost similar size. I hope you got it. I hope you got it. I hope you got this concept. Okay? But whatever concept I'm telling you, it is not valid to the scandium group. Why is that? It is not valid to scandium group. For scandium group, normally size increases. Scandium, then Y has got more size, then lanthanum has got more size. The size order here is lanthanum followed by Y followed by scandium. This is the actual order for this particular group. Why is that? Why is that? Why is that? Because lanthanoids, they come after lanthanum, right? They come after lanthanum. So, till lanthanum, there is no lanthanoid contraction. Lanthanoid contraction starts after this, right? It starts after this. So, for this particular group, size shows the normal order, as you can see. But remaining all, this is what it is. Okay? Look at this one as well. In your group 13, boron, aluminium, gallium, indium, and thallium. Okay? On moving from top to bottom, what should happen normally? Size should increase. Size should increase. This is expected. This is expected, right? This is expected. No doubt, from boron to aluminium, size is increasing. Size is increasing. But when you move from aluminium to gallium, What is happening exactly? Before gallium, there comes d block elements. Before gallium, there comes your 10 d block elements. Okay? Before gallium, there comes your 10 d block elements, in which the outer electron goes in d orbital. D, 4 shielders. 4 shielders means more effective nuclear charge, lesser size, right? Lesser size. So normally, gallium should have more size than aluminum, but due to ineffective shielding of d electrons, gallium has got lesser size than aluminum. Gallium has got lesser size than aluminum. Okay? Gallium has got lesser size than aluminum. Perfect? And the order finally becomes like this. This is the actual order. This is the actual order. What was the expected order? Boron should have least, right? Then comes your gallium. Just a second. Okay. Then comes your aluminium, indium, and thallium. This is the actual order of the size. Okay? Reason I believe you all know. Reason is due to the poor shielding of d electrons, right? Due to the poor shielding of d electrons in case of gallium, I would say size decrease for gallium. Is it clear? Is everything clear till here? Is everything clear till here? Can you tell me the answer of this question quickly? Can you tell me the answer of this question quickly? Everyone in the chats. You have to arrange them on the basis of size. Guys, few minutes back only I told you. More the positive charge. More the positive charge. More the effective nuclear charge. Lesser the size. Right? Majority is coming up with option B. Let me see. Yes, it's option B. Done. I believe this is clear. Chalo, let's move on to one more concept now. That is your ionization energy. We are left with 2 to 3 topics and we are done. Okay. We are left with 2 to 3 topics and we are done with class 11th inorganic. S block is not in the syllabus. Hydrogen is also not in the syllabus. It's not going to take more than 1.5 hours. Okay, so don't worry. So let's have a look on the new term. That's your ionization energy, right? Ionization enthalpy. There are solid state and states of matter. Are you the JE aspirant? I think you are the JE aspirant. Because solid state and states of matter is not in the NEET syllabus anymore. In your class 11th inorganic, there are only 2 chapters, periodic classification and chemical bonding. Thank you, Maharaj sir. Yeah. P block is in class 12th. P block not in class 11th, guys. That's class 12th. If you want to see the solid state and states of matter, I have taught that too on this channel itself. You just search it, states of matter by Wassim sir or solid state by Wassim sir, you'll get that. Okay. Chalo, I'm moving on to the ionization energy. Guys, how do we define exactly the ionization energy? How do we define the ionization energy? The minimum amount of energy which is required to remove the most loosely bonded, the minimum amount of energy which is required to remove the most loosely bonded outermost electron in ground state from the isolated gaseous atom. So if you'll be having the isolated gaseous atom, if you'll be having the isolated gaseous atom, let's say this is your isolated as well as the gaseous atom. This is the isolated atom in gaseous state, for example, right? Now, if you look at this particular electron, it is the most loosely bound electron. Now, in order to, since no doubt it is most loosely bound, but still nucleus will be attracting it towards itself. So in order to remove this, in order to knock out this electron, right, we have to break this attraction. How do we break this attraction? By supplying energy. So the minimum amount of energy which is required, to knock out, to take the most loosely bound electron out from the isolated gaseous atom is what you call as ionization energy. For example, you have got the gaseous isolated atom, right? You are providing it the ionization energy. So that means you are taking one electron out, the most loosely bound, right? And this metal gets converted into what? It gets converted into M positive. Perfect. Very much simple. The minimum amount of energy which is required to knock out the most loosely bound electron, right, from the influence of the nucleus is what you call as ionization energy. Now have a look over here. Let's say you've got the metal in gaseous state, right? For example, you are providing it energy and it's getting converted into M positive gas and it's giving one electron. You are taking out the most loosely bound electron from the isolated gaseous atom. The amount of energy required in this case is what I call as ionization energy 1. Okay. Now, if you take M positive, let's say you are taking an electron out from M positive gas. So it gets converted into M di positive gas. Let's say you are taking electron out from M positive. So the amount of energy required in this case is what you call as second ionization energy. Similarly, from M di positive gas, you are taking an electron out and it's getting converted into M tri positive gas. The amount of energy required in this particular case is what you call as ionization energy 3. Now, it's pretty much simple. In the first case, you are taking electron out from M. In the second case, you are taking electron out from M positive. In the third case, you are taking electron out from M di positive. So earlier it was M. Then you are taking electron out from M di positive. Then you are taking electron out from M di positive. Right? So from M to M positive. From M positive to M di positive, what happens to Z effective? Effective nuclear charge increases. If effective nuclear charge increases, that means from the last case, it is very difficult to take the outermost electron out. Because in the last case, effective nuclear charge will be maximum. More the positive charge, more the effective nuclear charge. More effective nuclear charge means more energy has to be required to knock out the most loosely bound electron. Right? So can I say in short, let's not go into very much depth. Can I say in short, ionization energy 3 is always greater than that of ionization energy 2, which is greater than that of ionization energy 1. Can I say something like this? Right? Perfect. And this is always, guys, always the third ionization energy is maximum, followed by second, followed by first. Okay. Now the point is, what are the factors? What are the factors that affect the ionization energy? First factor is pretty much simple, the effective nuclear charge, right? More the effective nuclear charge, That means there'll be more attraction between nucleus and its electron. So in order to take the electron out, we have to supply more energy. That means more is going to be the ionization energy. So ionization energy is simply directly proportional to what? Z effective. And Z effective, already we know that is directly proportional to positive charge, inversely proportional to negative charge. So you can tell me the answer here, Fe tri positive, Fe di positive, Fe. From where, if you want to take the electron out here, or you want to take the electron out here, or you want to take electron out here, where is the amount of energy required maximum? In the first case, because in the first case, effective nuclear charge is more. In the first case, effective nuclear charge is more. I hope this is clear to everyone. Right? So this is the first factor on which your ionization energy depends. Now, your ionization energy depends on one more thing. From which orbital you are taking the electron out? From which subshell you are taking the electron out? You must have heard your half-filled configurations like P3, D5, F7. These are half-filled configurations. And fully filled, P6, D10, F17, right? Your half-filled configurations and fully filled configurations, they are considered to be very stable. They are considered to be very stable. So to take the electrons out, from half-filled configuration or fully filled configuration, more energy is required. To take the electrons out from half-filled configuration or fully filled configuration, more energy is required. That means more is the ionization energy if electron has to be taken out from half-filled configuration or fully filled configuration. Okay, like you have got nitrogen, oxygen. What is the outermost configuration of nitrogen? 2p3. Outermost configuration of nitrogen is 2p3. So one here, and one here. What is the outermost configuration of oxygen? It's 2p4. 1, 2, 3, and 4. 2p4. This one is half-filled configuration. This is partially filled. This is partially filled. Half-filled configurations are very stable due to exchange energy, right? Half-filled configurations are very stable. So in order to take the electron out from here, more energy is required. So directly you can say ionization energy of nitrogen, first ionization energy of nitrogen would be more than that of the first ionization energy of oxygen, right? Because nitrogen has got half-filled configuration. Okay, if I want to compare the second ionization energy of nitrogen and oxygen, if I want to compare the second ionization energy of nitrogen and oxygen, for example, I'm writing nitrogen here, I'm writing oxygen. Okay, first ionization energy means you are taking the electron out from 2p3, here you are taking the electron out from 2p4. When you take the electron out from 2p3, it becomes N positive with configuration as 2p2. After you take the electron out from here, it becomes O positive with the configuration 2p3. And the energy required in this case here is what I call as ionization energy first of nitrogen. This I call as ionization energy ionization energy first of oxygen. Perfect. Now, if I want to compare the second ionization energy of nitrogen means you have to take electron from here so that it gets converted into N di positive. Second, the amount of energy required in this particular case is what I call as IE2, right? If I give IE2 here, it becomes O di positive. Perfect. Now compare the second ionization energy of nitrogen and oxygen. When you talk about the second ionization energy of nitrogen, electron has to be taken out from 2p2 configuration. But here, electron has to be taken out from 2p3 configuration. 2p3 configuration is half-filled, so more stable, more energy is required. So second ionization energy of oxygen is more than that of the second ionization energy of what? It is more than that of second ionization energy of nitrogen. Is this particular point clear? The second ionization energy point. Is it clear, guys? Is it clear? Clear to everyone? Yes? Amazing. Now, this is the question which has been frequently asked in different examinations. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Arrange them on the basis of their ionization energies. Arrange them on the basis of their ionization energies. What is the normal trend? If I write lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? Normal trend says that on moving from left to right, ionization energy increases. So this is the normal trend. This is the expected order. This is the expected order of ionization energies. But is it the actual order? Is it the actual order? No. See, beryllium and boron, you have to interchange. Nitrogen, oxygen, you have to interchange. Why is that? Why is that? Because in beryllium, the outermost configuration is 2s2. Boron, outermost configuration is 2p1. Nitrogen, outermost configuration is 2p3. Oxygen, outermost configuration is 2p4. Right? So here, if you talk about your beryllium, what is happening? If you talk about your beryllium, in your beryllium, this is 2s carrying 2 electrons. Here you have got 2p carrying 1 electron. Here you have got 2p carrying 3 electrons. Here you have got 2p carrying 4 electrons. Perfect. Among these two configurations, which one is more stable? This is completely filled. This has got 2 electrons, right? Completely filled. So more energy is required here, right? Perfect. So that is the reason why beryllium has got more ionization energy than that of boron. Now among nitrogen and oxygen, here you have to take the electron out from 2p3 configuration, half filled. So more energy is required. So actual order becomes like this. Beryllium has got more than boron and nitrogen has got more than that of oxygen. So this is the actual order of ionization energies because of the reasons which I gave you already. I hope this is also clear to everyone. Okay? I hope this is also clear to everyone. Now this is pretty much simple. On moving from top to the bottom in the group, what happens to ionization energy? On moving from top to bottom, size increases. Size increases, ionization energy decreases, right? It decreases down the group. Size increase, ionization energy decreases. Now, what are the applications of ionization energy? Ionization energy, its first and the clear-cut application, what is that? It gives us the idea about the metallic character of an element. It gives us the idea about the metallic character of an element. First of all, when you talk about metals, what do metals do? Do they lose electrons or gain electrons? When you talk about your metals, they have got tendency to lose electrons. If metals have got tendency to lose electrons, that means their ionization energy would be low. When it comes to your non-metals, they have got tendency to gain electrons. So that means their ionization energy is high, right? So when you talk about metals, their ionization energy is low. So low ionization energy, more metallic. Low ionization energy, more metallic. So remember, metallic character, it's inversely proportional to the ionization energy. Okay? Low ionization energy, more metallic. Low ionization energy means easily element can lose electrons. Easily metal can lose electrons. If metal is losing electrons easily, that means its metallic character will be more. So remember this particular point, metallic character is inversely proportional to ionization energy, guys. Right? Similarly, if you talk about the reactivity of metals, how do you differentiate which metal is more reactive, which metal is less reactive? It's simple, guys. That metal which loses electron easily, will be more reactive. That metal which loses electron easily would be more reactive. Okay, so reactivity of metals is also inversely proportional to ionization energy. Lesser the ionization energy of the metal, easily it will give away electrons. The ease with which the metal gives away electrons, that defines the reactivity of the metals. I hope this is also clear. I hope this particular point is also clear. Now there are 3 points which you need to know. That is the stability of oxidation state. Stability of oxidation state. See guys, for example, where do I get the space? Here. For example, M is getting converted into M positive. I'm giving it the first ionization energy and getting converted into M positive. Now I have to convert M positive into M di positive. I'm giving here ionization energy 2. Okay, right? So here you can see there are 2 oxidation states of M. Here M is present in +1 oxidation state. Here M is present in +2 oxidation state. Okay, right? Here M is present in +1 oxidation state. Here M is present in +2 oxidation state. So +1 and +2. Low oxidation state, high oxidation state. Low oxidation state, high oxidation state. My dear students, remember, if the difference between IE2 and IE1, if the difference between IE2 and IE1, if it comes out to be 42.7 electron volts, sorry, what I was talking about, in case of sodium, the difference between IE1 and IE2 comes out to be 47.7 electron volts. Comes out to be 47.7 electron volts. Read this particular statement. If the difference between two successive ionization energies, of element is greater or equal to 16 volts, then the lower oxidation state is stable. See, sodium getting converted into Na positive into Na plus 2. So lower oxidation state is plus 1 for sodium. Higher oxidation state is plus 2 for sodium. Right? And the difference between IE1 and IE2 is coming out to be 42.7, which is greater than 16. So here in this particular case, which oxidation state of sodium would be stable? Lower oxidation state. Lower oxidation state is plus 1. So Na positive would be more stable than Na di positive. So remember, if the difference between two successive ionization energies comes out to be greater or equal to 16 electron volts, at that point of time, lower oxidation state of an element is considered to be more stable. Okay? Right? Similarly, guys, one more case. If the difference between two successive ionization energies comes out to be less or equal to 11 electron volts, at that point of time, higher oxidation states are more stable. For example, as you see, magnesium, we are giving it ionization energy 1, it is getting converted into Mg positive, and this Mg positive after giving IE2 is getting converted into Mg di positive. If, for example, IE2 minus IE1, comes out to be less or equal to 11 electron volts, then higher oxidation state is more stable. What are the oxidation states shown here? This is plus 1, this is plus 2. So magnesium is showing two oxidation states here, plus 1, plus 2. This is the lower oxidation state, this is the higher oxidation state. And when the difference between two successive ionization energies is less or equal to 11 electron volts, at that point of time, higher oxidation state is considered to be more stable. So Mg di positive would be more stable than that of Mg positive. Okay? Am I clear with this, guys? I hope this particular point is also clear. One more point, guys. For example, you have got an element whose first ionization energy is equal to 3 electron volt. Second ionization energy is equal to 10 electron volt. Third ionization energy is equal to 20 electron volt. Fourth ionization energy is equal to 200 electron volt. Its fifth ionization energy is equal to 205 electron volt. Can you tell me how many valence electrons the element has? This is again one more application of this ionization energy to check the valence electrons. Can you check it? Can you let me know? Let me know in the chats. People. Hello. Is it done? Guys, you should solve this. See guys, to take the first electron out, 3 electron volt is required, right? If this is the nucleus. To take the first electron out, 3 electron volt is required. To take the second electron out, 10 electron volt is required. To take the third electron out, 20 electron volt is required. But to take the fourth electron out, 200 electron volt is required. That means fourth electron won't be present in this particular shell. Fourth electron will be present closer. That means the penultimate shell. Do you understand? That's why the jump is more from here to here. So how many electrons are there in outermost shell? 3. 3 means valence electrons are 3. So the element has got 3 valence electrons. This is one more application of this particular case. Okay, this is one more application of your ionization energy. I hope this is clear. Guys, just give me a second. Okay, I hope this particular stuff is clear. Now we can easily identify all this stuff. This was your NEET 2019 question. Now I hope you can easily do it. Can you let me know quickly the answer? I've solved it. I've solved it few minutes back only. I've solved it few minutes back only. I've solved it few minutes back only. You should know the answer now. You should remember the answer now. Beryllium's ionization energy would be more than that of borons, and nitrogen's would be more than that of oxygen. So it has to be option B, clearly. It has to be option B, clearly. Okay, it has to be option B, clearly. Can you tell me the answer of this question? What do you think? First, second, third, fourth, fifth ionization potentials are given. The element is likely to be. See, first is 7.1, 14.3, 34. See, where is the jump more? I can see jump is more here. 46.8 to 162.2. Right? So, it should have 4 valence electrons. 1, 2, 3, and 4. 4 valence electrons. Which of the following has got 4 valence electrons? Silicon. Right? Silicon has got 4 valence electrons. Perfect. Okay, the next cases are electron affinity. The next point is our electron affinity. How do we exactly define the electron affinity? Electron affinity is defined as the amount of energy which is released. The amount of energy which is released when an extra electron is added to the valence shell of an isolated gaseous atom. The amount of energy which is released when an extra electron is added to the isolated gaseous atom. Okay? See guys. See, understand. For example, this is the nucleus and these are the respective shells. Let's say there is electron here in this atom. Perfect. Now guys, let's say this is one incoming electron. This is one incoming electron. When this incoming electron will be coming closer to this atom, I would say there will be two things will arise here. First thing, this nucleus would be attracting this electron towards itself, the force of attraction. Okay. Then there will be a repulsion between these two electrons. There will be repulsions too. I'll say if attractions dominate, if attraction dominates, at that time electron gets added. Right? If attractions dominate, at that point of time electron gets added. Okay? At that point of time electron gets added. Right? And when attractions dominate, energy is released too. The amount of energy which is released when an extra electron is given to the isolated gaseous atom, right? That amount of energy is what you call as electron affinity. That's what you call as electron affinity. That's what you call as electron affinity. Now, for example, there is one more case as well. If repulsion dominates, will energy be released? Will energy be released when to add this electron? It's pretty much simple. If repulsions dominate here, energy is required to add this electron at that time. Energy is required at that time. Energy is required at that time. Right? If attractions dominate, energy is released. If repulsions dominate, energy is absorbed. Okay? Energy is absorbed. So what is electron affinity in short? It is the amount of energy released. It is the amount of energy released when an electron is added to the isolated gaseous atom. Okay? Right? Now guys, try to understand. The first electron addition in an atom. See, generally the first electron addition of an isolated gaseous atom is exothermic. So imagine this is your isolated gaseous atom and you are giving it the first electron, right? Okay. So energy is released in this particular case. So first electron gain enthalpy, if I say first electron gain enthalpy is always negative. I mean, it's generally negative, the first electron gain enthalpy. The first electron gain enthalpy is generally negative. But when it comes to second electron gain enthalpy means X negative you got, and you are giving one electron to this, right? It gets converted into X di negative. Perfect. So this is already negative. Now you are giving it one more electron. Negative will ripple. So energy won't be released here. Energy will be absorbed. So electron gain enthalpy 2, right? Electron gain enthalpy 1 was negative. Now electron gain enthalpy 2 would be positive in nature. Electron gain enthalpy 2 would be positive in nature. Perfect. So first electron, in the first case, when first electron is added to the isolated gaseous atom, generally energy is released. But when it comes to second, energy is absorbed. Right? So in the second electron gain enthalpy, it is always positive. It's always positive. Now, you can have a look on this particular stuff as well. For example, I've got oxygen. I'm giving one electron to oxygen, right? Energy is released in this particular case. How much? 141 kilojoules. Now you got O negative. You are giving it one more electron. It got converted into O di negative. So during this particular process, energy would be absorbed. Okay? Energy would be absorbed. And if you add these reactions, you'll be getting this as the final reaction. And in this final reaction, what would be the enthalpy change? How you got this final reaction? By adding these two, right? If you are adding these two, that means you have to add these delta H values as well. And this is the final answer of this for this particular process. I hope this is also clear. Right? So basically the first electron gain enthalpy is negative. Second electron gain enthalpy is positive, right? First one is exothermic. Second one is going to be endothermic automatically. Now the factors which affect electron affinity. What are the factors? First factor is going to be the size. For example, this is one atom. This is one more atom. This is its nucleus. You have got electron here. you have got electron here, right? Where will be attraction between nucleus and electron more? Attraction between nucleus and electron will be more here because distance is less, right? More the attraction, more the energy released. More the energy released means more is electron gain enthalpy. So I would say electron gain enthalpy is inversely proportional to size. Or you can say electron affinity is inversely proportional to size. Lesser the size, more the electron affinity, more the energy released. Okay? Simple thing. There is not a lot of things to explain here. Second is your electron affinity. It is directly proportional to effective nuclear charge as well. More the effective nuclear charge of an atom. That means more is the tendency of the nucleus for the incoming electron. More tendency of the nucleus for the incoming electron means more attraction between nucleus and incoming electron. More energy released. More energy released means more electron affinity. Simple. It's again directly proportional. Again directly proportional, guys. That's it. Again directly proportional. And I would say electron affinity is directly proportional to effective nuclear charge. And effective nuclear charge already, we know that it's directly proportional to positive charge, inversely proportional to negative charge. That's something which we have discussed. Okay? What is the general order? What is the general order of electron affinity? What do you think? On moving from left to right. On moving from left to right. What happens to size? Size generally decreases. If size decreases, electron affinity would be increasing. On moving from left to right. Okay? Similarly, on moving from top to bottom, what happens to size? Size increases. Therefore, electron affinity generally decreases. Because electron affinity, that's inversely proportional to size. Because electron affinity, that is inversely proportional to size. Okay? That's inversely proportional to size. Now, for example, you have got group 17, fluorine, chlorine, bromine, iodine, right? On moving from top to bottom, size increases. Size increase, that means electron affinity should decrease. So, electron affinity should decrease. This is the expected order. This is expected, right? So, I would say fluorine should have more electron affinity than chlorine. This is expected. Fluorine should have more electron affinity than that of chlorine. But the case is reverse. The case is reverse. The actual order is chlorine has got more electron affinity than fluorine. This is the actual order. This is the actual order. Why is that? See, if you talk about fluorine, fluorine has got lesser size, smaller size. Smaller size means more electron density. Smaller size means more electron density. If there is more electron density on fluorine, when incoming electron comes, so there will be repulsion. There will be repulsion between more electron density and this incoming electron. If there is repulsion, that means this fluorine, it won't be having a lot of affinity towards incoming electron as what chlorine would be showing, right? So remember, chlorine has got more electron affinity than that of fluorine. Similarly, in case of when you talk about oxygen, sulfur, down the group, it should decrease, but here also it increases. Sulfur has got more electron affinity than that of oxygen. The reason is again the similar. Oxygen, due to its smaller size, it has got more electron density, so lesser electron affinity, right? Lesser electron affinity. So I would want you guys to remember these three orders because they are very important. These three orders are very important, right? One is for group 17, one is for group 16, and one is for group 14. These three orders are very, very, very important. Anything can be asked out of these. Okay? Anything can be asked out of these. Anything can be asked out of these. Right, guys? There is one thing which I would want to share with you. What is that? See, guys, this is a neutral atom. It's a neutral atom. I'm giving one electron to it. When I give one electron to it, right, it gets converted into X negative. It gets converted into X negative. So I'm giving one electron to X, this neutral atom, right? The amount of energy released in this process is what I call as electron affinity of X gas. Is what I call as electron affinity of X gas. Now, if I reverse this reaction means I've got X gas negative it gives X gas plus 1 electron. In this particular reaction, what do you observe? Do you observe I'm taking 1 electron out? I'm taking 1 electron out, right? So in this particular process, if you are taking electron out, energy is absorbed or released? Energy is absorbed in this particular case because you are taking the electron out. If energy is absorbed in this particular case, if energy is absorbed, so this particular process I'll be calling as ionization energy of X negative. Ionization energy of X negative. In the first process, energy is released. In the second process, energy is absorbed. In the first process, energy is released. In the second process, energy is absorbed. I would say, since both the processes are same, it is just I've reversed them. I would say electron affinity of X gas. Electron affinity of X gas would be equal to what? It would be equal to ionization energy of X negative gas. Okay? Since they are the reverse processes. So whatever energy is released here in this process, same amount of energy is absorbed here in this process. Right? Same amount of energy is absorbed in the next process. That's it. That's it. Why did I give you this particular point here? Because once a question was asked on this in your JEE examination. The question was like this. The question was like this, and I believe you can easily do it. What is the question? What is the value of electron gain enthalpy of Na positive? If ionization energy of sodium means Na gas gives Na positive gas plus 1 electron. This is what I call as ionization energy. Ionization energy of sodium is how much? 5.1 electron volt. What do I need to calculate? Electron gain enthalpy of Na positive. Electron gain enthalpy of Na positive. Gain enthalpy of Na positive means Na positive gas plus 1 electron gives sodium. Do you see this particular reaction is just reverse of this? Right? It is just reverse of this. So, in this particular case, how much energy is absorbed? 5.1. In this particular case, how much energy will be released? 5.1 electron volts will be released. Energy release means delta H value has to be negative. So, it is minus 5.1 electron volts. Right? It is minus 5.1 electron volts. Okay? One last topic, guys, that is electronegativity. But this is something which you are going to do on your own because it's a matter of one slide, right? I'll share the PDF of this particular session in the Telegram. If you are not the part of Telegram, be the part of Telegram. It is, the name of Telegram channel is Wassim but Chemistry Official. This is the name of the Telegram channel. Okay? Perfect. So tell me once in the chats whether whatever things I've discussed in the today's session, are all the things clear? Honestly, you can let me know. Vishnu, that won't be discussed here. Just let me know in the chats quickly. Whatever things I discussed in the chats, whatever things I discussed in the today's session, are all the things clear? Yeah? Perfect. That's great. Yes, the session is completed. This PDF I'll be sharing in the Telegram, right? Notes I'll be sharing in the Telegram. Next marathon is going to be for your class 11th physical chemistry. And that's going to be a long, long marathon because its syllabus is a lot. Okay? So in the comment section, I would want one thing from you. That is class 11th inorganic done and dusted. Okay? In the comment section, I would want this from all of you. Class 11th inorganic done and dusted. Perfect. Chalo guys, I'm taking a leave with this. I'll see you all in the next session. Huh? You take care. Bye-bye. God bless you all.